Welcome to Level 1 of 100 Paradoxes. Let's start with a simple yet mind-bending question. Imagine there is a town with only one barber. This barber follows a strict rule. He only shaves those who do not shave themselves. If a man in the town shaves himself, the barber does not shave him. But if he does not shave himself, the barber must shave him. Seems simple, right? But now, here's the paradox. Who shaves the barber? Let's analyze both possibilities. First, suppose the barber shaves himself. But according to the rule, he can only shave those who do not shave themselves. That means he shouldn't be shaving himself. Now, let's assume the barber doesn't shave himself, but in that case, he follows his rule and must shave anyone who doesn't shave themselves, which includes himself. Both possibilities contradict each other. If he shaves himself, he shouldn't. If he doesn't, he should. So, what's the solution? The paradox exposes a logical flaw in the rule itself. It suggests that such a barber cannot logically exist. Any attempt to define him within this system leads to contradiction. And that's Level 1. Welcome to Level 2 of 100 Paradoxes. This one is deceptively simple but incredibly profound. It's called the liar paradox. Imagine someone writes down a sentence on a piece of paper. The sentence reads, "This statement is false." Now, let's analyze it logically. If the statement is true, then what it says must be correct. But the statement says that it is false. That means it cannot be true. Okay? So, let's assume instead that the statement is false. But if it's false, then its claim that it is false must be incorrect. That means it must actually be true. And just like that, we're stuck in an endless loop. The statement cannot be true, but it also cannot be false. No matter how we look at it, we are trapped in a logical contradiction. And that's Level 2. If you think this paradox is tricky, just wait. Things are only going to get weirder. Welcome to Level 3 of 100 Paradoxes. This one comes from ancient Greece and challenges our understanding of motion and time. It's called Zeno's Achilles and the Tortoise Paradox. Imagine a race between Achilles, the great Greek warrior, and a slow-moving tortoise. To make things fair, the tortoise gets a head start, let's say 10 meters ahead. Achilles is much faster, so you would think he should easily overtake the tortoise. But Zeno argued that Achilles can never actually catch up. Here's the reasoning. First, Achilles reaches the point where the tortoise started, but in that time, the tortoise has moved forward a little bit. Next, Achilles reaches that new position, but again, the tortoise has moved slightly ahead. This keeps happening indefinitely. Every time Achilles gets to where the tortoise was, the tortoise has inched forward. Even though the distances get smaller and smaller, there are infinitely many steps Achilles must take. So, according to Zeno, Achilles is stuck in an infinite sequence and can never actually reach the tortoise. Of course, in reality, we know that Achilles will easily overtake the tortoise. So, what's wrong with Zeno's reasoning? The paradox comes from the idea that dividing distance into infinite smaller parts means infinite time is needed to complete them. But in reality, an infinite series can have a finite sum. The time Achilles takes in each step gets shorter and shorter, and all the steps together add up to a finite amount of time. This paradox puzzled philosophers and mathematicians for centuries until the development of calculus. Mathematicians like Newton and Leibniz showed that infinite sequences can converge to a finite number, resolving the paradox. But Zeno's paradox still raises deep questions about the nature of time, space, and motion. Is motion continuous, or does it happen in discrete jumps? If space is infinitely divisible, does that mean reality itself is made of infinite steps? Welcome to Level 4 of 100 Paradoxes. This one is called the unexpected hanging paradox, and it messes with our understanding of logic and predictions. Imagine a judge tells a prisoner, "You will be hanged at noon on a weekday next week, but the exact day will be a surprise. You won't know which day it is until the executioner arrives at your cell that morning." The prisoner thinks carefully and realizes something. If the hanging were to happen on Friday, then by Thursday night, he would know, because Friday is the only day left. But that would ruin the surprise. So, it can't happen on Friday. Now that Friday is ruled out, he thinks about Thursday. If the hanging were to happen on Thursday, he would realize it by Wednesday night, because Friday is already eliminated. But since it must be a surprise, that means Thursday is also impossible. Using the same logic, he eliminates Wednesday, then Tuesday, and finally Monday. Eventually, he convinces himself that the hanging cannot happen at all. Feeling relieved, the prisoner sleeps peacefully through the week. Then, on Wednesday, the executioner arrives, and the prisoner is completely shocked. The judge was right. The hanging was a surprise. So, what went wrong with his reasoning? The paradox comes from the conflict between logical deduction and surprise. The prisoner assumed that if he could eliminate every possible day, then the hanging couldn't happen. But that reasoning falls apart when the actual event defies his expectations. Welcome to Level 5 of 100 Paradoxes. This one is called the Crocodile Paradox, and it's all about logic, predictions, and a very tricky dilemma. Imagine a cunning crocodile lurking by the riverbank. One day, it grabs a child. The desperate parent begs for the child's return. The crocodile, being unusually logical, makes a deal. It says, "I will return your child if and only if you correctly predict what I will do next." Now, the parent thinks carefully and makes a prediction. "You will not return my child." Now, the crocodile is stuck in a paradox. If the prediction is correct, then the crocodile must return the child, since that was the deal. But if the crocodile returns the child, then the prediction was actually wrong, because the parent said the child would not be returned. On the other hand, if the prediction is wrong, then the crocodile doesn't have to return the child. But that means the prediction was actually correct, because the parent said the child wouldn't be returned. The crocodile is now trapped in an endless loop. No matter what it does, it contradicts itself. This paradox plays with self-referential logic, much like the liar paradox. It shows how reasoning that seems logical can lead to contradictions when it involves predictions about itself. Philosophers use paradoxes like this to explore language, logic, and decision-making. It also appears in discussions about contracts, ethics, and even artificial intelligence, because how do you program a system to handle contradictory conditions? Welcome to Level 6 of 100 Paradoxes. This one is called the Ship of Theseus Paradox, and it challenges our understanding of identity and change. Imagine an ancient ship, the Ship of Theseus, docked in a harbor. Over time, its wooden planks begin to rot, so they are replaced one by one with brand new planks. This process continues for years until, eventually, every single piece of wood has been replaced. Now, here's the question. Is it still the same ship? At first, it seems like the answer is yes. After all, the ship remained the same in form and function. It was just repaired gradually. But let's add a twist. Imagine that someone took all the old discarded planks and reassembled them into a ship identical to the original. Now we have two ships. One, the ship made from the new planks, still sitting in the harbor. Two, the ship made from the original planks, now reconstructed elsewhere. Which one is the real ship of Theseus? If the first one is the real ship, that means an object can change all of its parts and still remain the same. But if the second one is the real ship, then that suggests identity is tied to its original materials rather than its continuous existence. This paradox forces us to question what it means for something to remain the same over time. It applies not just to ships, but to people, objects, and even consciousness. For example, every cell in the human body is replaced over time. If all your cells change, are you still the same person? If we could transfer your brain into a different body, would you still be you? The Ship of Theseus paradox has been debated by philosophers, scientists, and even neuroscientists studying personal identity. It's also an important question in technology. If we replace every part of a machine, is it the same machine or a completely new one? Welcome to Level 7 of 100 Paradoxes. This one is called the Grandfather Paradox, and it's one of the most famous paradoxes in time travel. Imagine you invent a time machine. You decide to go back in time to when your grandfather was young, before he ever met your grandmother. For some reason, you decide to prevent them from meeting, or, even worse, you accidentally cause your grandfather's death before he has any children. Now, here's the problem. If your grandfather never had children, then your parent was never born. And if your parent was never born, then you were never born. But if you were never born, then how did you go back in time in the first place? This creates a paradox. By changing the past, you erase your own existence. But if you never existed, You could never have gone back in time to change the past in the first place. So, what happens? There are several possible explanations that scientists and philosophers have proposed. Time fixes itself. Some theories suggest that history resists change. No matter what you do, something will always prevent you from altering the past in a way that causes contradictions. Maybe your gun jams, or you get distracted, or events unfold in a way that stops you from affecting your grandfather's future. The many worlds interpretation. Instead of creating a contradiction, your actions create a new timeline or parallel universe where you were never born. In your original timeline, nothing changes, but in the new one, you simply don't exist. You just vanish. If you do succeed in preventing your own birth, some theories suggest you would simply disappear from existence as if you never existed in the first place. But that brings up another question. If you vanish, who changed the past? The grandfather paradox is one of the biggest challenges to theoretical time travel. It suggests that traveling back in time and changing the past might be logically impossible, or at least far more complicated than it seems. This paradox has been explored in movies, books, and scientific discussions, and it's a key argument in the debate over whether time travel could ever be possible. Welcome to Level 8 of 100 Paradoxes. This one is called the Sorites paradox, also known as the paradox of the heap, and it challenges the way we define vague concepts. Imagine you have a heap of sand made up of millions of grains. Now, remove one grain from the heap. It's still a heap, right? Now remove another grain. It's still a heap. Keep going, grain by grain. At what exact point does it stop being a heap? If you remove just one grain, it doesn't seem like a heap suddenly disappears. But if you keep removing grains, eventually, you'll be left with only one grain of sand, which is definitely not a heap. So, where did the heap go? This paradox exposes a problem with vague concepts. Words like heap, bald, or tall don't have clear boundaries. For example, if a man has a full head of hair and starts losing hair one by one, when does he become bald? If a child grows an inch every year, at what exact height does tall begin? Because these concepts are fuzzy, they create logical contradictions. Philosophers have debated solutions for centuries, but there's no clear answer. Some approaches include 1. The sharp cutoff theory. Some argue that even vague terms have hidden exact boundaries, even if we don't know them. Maybe a heap is exactly 1,000 grains of sand or more, and anything less is not a heap. 2. The continuous spectrum. Others argue that concepts like heap and bald exist on a spectrum, and trying to force an exact cutoff is pointless. 3. Supervaluationism. A more complex solution suggests that vague terms can be true in some cases, false in others, and indeterminate in between, depending on context. The Sorites paradox isn't just a word game. It affects law, ethics, and artificial intelligence. How do we define when a person officially becomes an adult? When does a collection of actions become a crime? How does an AI determine the difference between big and small when no clear boundary exists? Welcome to Level 9 of 100 Paradoxes. This one is called the Omnipotence paradox, and it challenges the very idea of unlimited power. Imagine a being that is all-powerful, a being that can do anything. Now, here's the paradox. Can this being create a rock so heavy that it cannot lift it? Let's break it down. If the being can create such a rock, that means there is something it cannot do, lift the rock. But if it cannot create the rock, then there is also something it cannot do, create the rock in the first place. Either way, there is something it cannot do, which contradicts the definition of omnipotence. This paradox has been debated for centuries in philosophy, theology, and logic. It raises the question, what does it mean to be all-powerful? Some philosophers attempt to resolve the paradox in different ways. 1. Redefining omnipotence. Some argue that omnipotence doesn't mean the ability to do the logically impossible. Just as a square circle can't exist, an all-powerful being wouldn't need to create a rock it can't lift, because the question itself is nonsensical. 2. The self-limitation theory. Others argue that an omnipotent being could choose to limit its own power, meaning that creating such a rock is possible, but lifting it would be voluntarily impossible. The omnipotence paradox ties into deep questions about the nature of power, logic, and even the structure of reality. If true omnipotence creates contradictions, does that mean even power must obey logic? And if so, is logic itself more fundamental than power? Welcome to level 10 of 100 paradoxes. This one is called the Raven Paradox, and it challenges the way we think about evidence and logic. Imagine a simple scientific statement: all ravens are black. At first, this seems easy to test. If you observe a black raven, that confirms the statement, right? But what about other things, like a red apple? Here's where the paradox begins. According to logic, the statement all ravens are black is equivalent to saying everything that is not black is not a raven. This means that if you see a red apple, it is technically confirming that non-black things are not ravens, which, in turn, seems to support the idea that all ravens are black. So, does seeing a red apple actually provide evidence that all ravens are black? That seems absurd, but logically it follows. This paradox was introduced by philosopher Carl Gustav Hempel, and it reveals a strange problem in how we define scientific confirmation. Normally, we think of evidence as something that directly supports a claim, but in this case, a completely unrelated object, a red apple, somehow becomes evidence about ravens. Philosophers and scientists have debated solutions to this paradox. 1. Rejecting equivalence. Some argue that even though the two statements are logically the same, they don't work the same way in real-world reasoning. Seeing a single red apple doesn't really tell us anything about all ravens. 2. Bayesian probability. Others argue that while a red apple does technically provide evidence, the effect is so tiny that it's practically meaningless compared to actually observing black ravens. 3. Reevaluating evidence. Some suggest that we need to rethink how we define confirmation. Maybe evidence should only come from directly observing what we're testing, rather than relying on indirect logic. The Raven Paradox challenges our basic assumptions about scientific reasoning, probability, and logic. If seeing a black raven and seeing a red apple both count as evidence, then what really counts as proof? Welcome to level 11 of 100 paradoxes. This one is called the Preface Paradox, and it challenges how we think about knowledge and belief. Imagine an author has just finished writing a book filled with carefully researched facts and arguments. They have checked every source, reviewed all the evidence, and are fully confident that each statement in the book is true. However, in the book's preface, the author writes something like this: "Despite my best efforts, there may still be some mistakes in this book." Now, here's the paradox. The author believes every individual statement in the book is true, but at the same time, the author also believes that at least one statement is probably false. How can both beliefs be true at the same time? If the author is rational, they should acknowledge that human errors happen, even in well-researched books. But if they truly believe there is a mistake, which statement do they doubt? If they doubted any specific statement, they should remove or correct it. This paradox reveals a fundamental problem in knowledge and probability. It shows that 1. We can believe multiple things at once, even if they seem contradictory. 2. Rational belief doesn't always mean absolute certainty. 3. Acknowledging the possibility of being wrong is itself a rational belief. Philosophers and logicians have debated this paradox in relation to epistemology, the study of knowledge. It connects to Bayesian probability, where beliefs are based on probability rather than absolute truth. For example, if a scientist publishes research, they trust their conclusions, but also know that new evidence could prove them wrong in the future. This is what makes science self-correcting. Progress happens because we acknowledge uncertainty. The preface paradox forces us to ask, how much confidence should we have in our own knowledge? Can we ever be completely certain of anything? Welcome to level 12 of 100 paradoxes. This one is called the Paradox of the Court, and it's a paradox about promises, contracts, and legal loopholes. Imagine an ancient Greek philosopher and lawyer named Protagoras. He agrees to take on a student named Euthylos and teach him law. But since Euthylos cannot afford to pay up front, they make a deal. Euthylos will only pay Protagoras if he wins his first case. After completing his studies, Euthylos decides not to take any cases at all, meaning he never wins or loses a case. As time passes, Protagoras becomes frustrated and takes Euthylos to court to force him to pay. And this is where the paradox begins. Protagoras' argument: If Euthylos loses this case, then the court has ruled against him, and he must pay as part of the verdict. If Euthylos wins the case, then he has won his first case, meaning he now has to pay Protagoras according to their original agreement. Either way, Protagoras argues, Euthylos must pay. Euthylos' argument: if he wins the case, the court has ruled that he doesn't have to pay. If he loses the case, then he has still never won a case, meaning the original agreement says he doesn't have to pay. Either way, Euthylos argues he does not have to pay. Each side has a perfectly logical argument that contradicts the other. If the court rules in favor of Protagoras, that means Euthylos must pay, but that means he has won his first case, which means he shouldn't have to pay. If the court rules in favor of Euthylos, that means he has won the case, which means he should pay. So, who actually wins? This paradox highlights loopholes in contracts, legal reasoning, and self-referential logic. It also raises deeper questions about how rules and agreements function in the real world. If a contract creates an unsolvable contradiction, how should it be enforced? Even today, courts sometimes face self-referential legal dilemmas where contracts, laws, or rulings create logical paradoxes. Welcome to level 13 of 100 paradoxes. This one is called the lottery paradox, and it challenges the way we think about rational belief and probability. Imagine a fair lottery with 100,000 tickets. Only one ticket will win, and each ticket has a 1 in 100,000 chance of winning. Now, consider the following reasoning. The chances of any one specific ticket winning are incredibly low, just 0.001%. Since the probability of winning is so tiny, it seems rational to believe that each individual ticket will lose. But if we apply this reasoning to every ticket, that means we should believe that all tickets will lose. However, we know for a fact that one ticket must win. So we end up believing that every ticket will lose, even though we also know that one of them will win. How can we logically believe that each individual ticket will lose, while also knowing that one of them must win? This paradox exposes a deep problem in probability, logic, and belief systems. It shows that even when we make rational assumptions about individual events, those assumptions can contradict each other when applied to the whole system. Philosophers and logicians have explored different ways to resolve this paradox. 1. Rejecting certainty. Some argue that the problem comes from treating low probability as impossible. Just because something is unlikely doesn't mean we should fully believe it won't happen. 2. Contextual belief. Others suggest that belief isn't just about probability, but also about context. While it's reasonable to doubt each ticket individually, it's also reasonable to believe that one of them will win. 3. Probability versus knowledge. Another view is that probability-based beliefs work differently from absolute knowledge. We can rationally doubt each ticket while still knowing that one will win. The lottery paradox has implications for decision-making, artificial intelligence, and even real-world legal cases. It forces us to ask, what does it mean to believe something? Can we hold beliefs that are individually rational but collectively contradictory? Welcome to level 14 of 100 paradoxes. This one is called the two envelopes paradox, and it challenges the way we think about logic, probability, and decision-making. Imagine you're presented with two envelopes. Inside each envelope is some amount of money, but you don't know how much. You are told that one envelope contains exactly twice as much money as the other. You randomly choose one envelope and open it. Inside, you find $100. Now, you are given a choice. Keep the $100. Switch to the other envelope, which has either $50 or $200. At first, it seems like a 50-50 decision. But let's analyze it further. Since you don't know whether you pick the higher or lower envelope, there are two possibilities. 1. If your envelope contains the smaller amount, $100, the other envelope has $200. 2. If your envelope contains the larger amount, $100, the other envelope has $50. You reason that if you switch, there's a 50% chance you double your money to $200. There's a 50% chance you lose half and end up with $50. Now, let's calculate your expected value if you switch. 50% chance of $200 plus 50% chance of $50 equals 0.5 times 200 plus 0.5 times 50 equals 100 plus 25 equals $125. Since the expected value of switching is $125, which is greater than the $100 in your hand, it seems like you should always switch. But here's the paradox. No matter which envelope you start with, the same logic applies. This means that before opening either envelope, you should always plan to switch. But that creates an infinite loop, since if you switch, the same reasoning applies again, meaning you should switch back. So, what's wrong with this logic? Mathematicians and philosophers have debated different ways to resolve the paradox. 1. Faulty probability assumption. The mistake comes from assuming a 50% chance that your envelope is the smaller one. In reality, the game isn't structured this way, so the math is misleading. 2. Undefined expectations. The expected value calculation only works if we know how the amounts were chosen, but since the envelopes are chosen arbitrarily, we don't have enough information to apply this formula. 3. No real advantage. Some argue that switching doesn't actually change your odds in a meaningful way, since you always return to the same paradox. The two envelopes. Paradox reveals flaws in decision theory, probability, and mathematical expectation. It's a great example of how logic that seems sound can lead to absurd conclusions. Welcome to level 15 of 100 paradoxes. This one is called Russell's paradox, and it's a problem that broke mathematics for a while. Imagine you have a list of things. Some lists include themselves, and some don't. A grocery list does not include itself. It just lists food. A list of all lists would include itself because it contains every list. Now, let's create a special list. The list of all lists that do not include themselves. Let's ask a simple question. Should this list include itself? If it includes itself, then it doesn't belong in the list, because the rule says it should only contain lists that don't include themselves. If it does not include itself, then it must belong in the list, because it fits the rule. No matter what, we end up with a contradiction. The list can't exist without breaking its own rule. This might sound like a word trick, but it actually caused a major crisis in mathematics when Bertrand Russell discovered it in 1901. At the time, mathematicians thought they could neatly organize all of math using sets, which are just groups of things. But Russell's paradox showed that their system had a flaw. Some sets create contradictions just by existing. To fix this, new rules had to be made, and modern math had to be redesigned to avoid this problem. Welcome to Level 16 of 100 Paradoxes. This one is called the potato paradox, and it's a surprising problem about percentages, weight, and how numbers can trick us. Imagine you have 100 kilograms of potatoes. These potatoes are 99% water by weight, meaning only 1% of their weight is actually solid potato. Now, you leave them out in the sun to dry. After some time, they lose water, and now they are only 98% water. Here's the question. How much do they weigh now? At first, you might think the potatoes have only lost a little bit of water. Maybe they now weigh 99 kilograms or 98 kilograms. But the actual answer is shocking. The potatoes now weigh only 50 kilograms. How is that possible? Let's break it down. Originally, the potatoes were 99% water, meaning the solid potato part made up 1% of 100 kilograms. That means the solid potato part weighed 1 kilogram, and the rest, 99 kilograms, was just water. Now, after drying, the solid part is still 1 kilogram, but now it makes up 2% of the total weight instead of 1%. So if 1 kilogram is now 2%, then the total weight of the potatoes must be 50 kilograms, because 1 kilogram is 2% of 50 kilograms. This paradox happens because percentages don't always behave the way we expect. When the water content decreases from 99% to 98%, it seems like a small change, but the actual amount of water lost is huge. The potato paradox is a great example of why we have to be careful when working with percentages, proportions, and assumptions. Even when the math is correct, the results can be completely unintuitive. Welcome to level 17 of 100 paradoxes. This one is called the arrow paradox, and it challenges how we think about motion and time. Imagine an archer shooting an arrow. The arrow flies through the air, moving toward its target. Now, let's freeze time for a moment and look at the arrow at a single instant. At that exact moment, the arrow is motionless. It isn't moving forward or backward. It's just there, occupying a single point in space. Now, imagine doing this at every single instant in time. At every moment, the arrow is just frozen in place. So, if the arrow is never actually moving at any instant, then how does it move at all? This is Zeno's arrow paradox, created by the ancient Greek philosopher Zeno of Elea. He argued that motion is an illusion because at any single moment in time, an object is standing still. If it's always standing still, then it never actually moves. Of course, in reality, we know the arrow does move, but this paradox shows a strange problem when we try to break time into infinitely small moments. Philosophers and scientists have tried different ways to solve this paradox. 1. Calculus and limits. Modern mathematics, especially calculus, explains that motion is the result of an infinite number of tiny changes over time. Even though the arrow is still in any instant, its position changes over many instants. 2. Quantum physics. Some physicists suggest that time may not be continuous but comes in tiny, indivisible units, so objects don't move smoothly but in incredibly small jumps. 3. Time as a process. Another view is that time isn't just a series of frozen moments, but a flowing process, and trying to divide it into single points misses the bigger picture. The arrow paradox forces us to ask, what is motion really? Is time made of individual moments, or is it something continuous? Even today, scientists and philosophers still debate the true nature of time. Welcome to level 18 of 100 paradoxes. This one is called the whole paradox, and it challenges how we think about the existence of nothing. Imagine you dig a hole in the ground. The hole is definitely there. You can see it, stand inside it, and measure its depth. But here's the strange question. Where is the hole? Is the hole something, or is it just the absence of something? Let's take it a step further. Suppose you fill the hole back up with dirt. Where did the hole go? Did it move somewhere? Did it disappear into nothing? This may sound like a silly question, but it highlights a deeper problem in language, logic, and physics. We talk about holes as if they are objects, but really they are just empty space, a lack of something rather than a thing itself. Philosophers and scientists have debated what it means for something to exist, if it's really just an absence of something else. The whole paradox connects to many deep questions. 1. Are holes real objects? Some argue that holes are not things themselves, they are just gaps in something else. A donut has a hole, but the hole isn't a separate object. It's just an empty part of the donut. 2. Do holes move? If you take a piece of cheese with holes in it and move the cheese, did the holes move too? Or did they stay in the same place and the cheese just moved around them? 3. Does nothing exist? In physics, space itself is often described as empty. But quantum mechanics tells us that even empty space has energy, fluctuations, and virtual particles appearing and disappearing. If nothingness is always filled with something, then does nothing even exist? The whole paradox makes us question how we define absence, emptiness, and reality itself. It might seem like just a fun word puzzle, but it actually connects to deep ideas in physics, philosophy, and mathematics. Welcome to level 19 of 100 paradoxes. This one is called Moore's paradox, and it's about a strange contradiction in how we express beliefs. Imagine someone says, "It is raining, but I don't believe it is raining." Something feels off, right? The sentence isn't a contradiction in pure logic. Both parts could be independently true. It could be raining. The person could genuinely not believe it's raining, but when put together, the sentence feels impossible to sincerely say. This is Moore's paradox, named after philosopher G.E. Moore, who noticed this strange problem in belief and language. Normally, when we state a fact, we assume we also believe it. But in this case, the speaker is claiming something while also denying that they believe it. It gets even weirder when we apply it to knowledge. I know this is true, but I don't believe it. How can you know something and not believe it at the same time? Doesn't knowing something require belief? Philosophers have debated possible explanations for Moore's paradox. 1. Belief and assertion are linked. Some argue that when you assert something, you're also implying that you believe it. Saying something while denying belief creates a hidden contradiction. 2. Self-defeating statements. Others suggest that statements like this are self-defeating because they break the normal way language works. Even if the sentence is logically possible, it goes against how humans communicate. 3. Cognitive dissonance. Moore's paradox is similar to cognitive dissonance, where a person holds conflicting beliefs. For example, someone might say, "Smoking is bad for me, but I don't believe it will hurt me." This paradox reveals that our minds don't always follow strict logic. Moore's paradox is important in philosophy, psychology, and artificial intelligence. If we ever create AI that thinks like humans, will it also struggle with paradoxes of belief? Can a machine say, "I know the answer, but I don't believe I know it"? Welcome to level 20 of 100 paradoxes. This one is called the twin paradox, and it's a mind-bending problem from Einstein's theory of relativity that challenges our understanding of time. Imagine two identical twins, Alice and Bob. Alice stays on Earth while Bob travels into space on a high-speed rocket moving close to the speed of light. After some time, Bob turns around and comes back to Earth. Now, here's where the paradox begins. From Alice's point of view, Bob was moving really fast, which means, according to Einstein's time dilation, time ran slower for him. So when Bob returns, he should be younger than Alice. But from Bob's point of view, it was Alice and Earth that were moving fast while he stayed still in his own frame of reference. So, shouldn't that mean Alice's time slowed down, making her the younger one instead? Each twin sees the other's clock moving slower. So, when they reunite, who is actually younger? This seems like a contradiction, but here's the resolution. The paradox is only an illusion because the situation is not truly symmetrical. Bob experiences acceleration and deceleration when turning his spaceship around, while Alice remains in a single, unaccelerated frame of reference. The acceleration breaks the symmetry of their experiences. The actual result, confirmed by real experiments, is that Bob will be younger than Alice when he returns. The faster he traveled and the longer he was gone, the greater the difference. This is a real effect of time dilation, and it has been observed with high-speed particles in physics experiments. Welcome to level 21 of 100 paradoxes. This one is called the paradox of self-amendment, and it raises a strange question about rules, laws, and logic. Imagine a legal system where there is a supreme law that says, this law can only be changed if a majority agrees to change it. So far, that seems reasonable, but now suppose the majority votes to change the rule itself, so that future laws can be changed without needing a majority. Here's the paradox. If the rule is truly unchangeable unless a majority agrees, then it should not be able to change itself. But if a majority does change it, then it proves that the rule was never truly unchangeable to begin with. This paradox appears in legal systems, constitutions, and philosophy. Some laws or rules claim to be fundamental and unchangeable, but if they can be changed by the very system they created, then are they truly absolute? This also applies to logic itself. What happens if we create a logical system with a rule that says, this rule cannot be changed? Can the system change its own rules? If it can, then the rule wasn't unchangeable. If it can't, then what happens if we need to fix a contradiction within the system? There are different ways to think about this paradox. 1. Hierarchical laws. Some legal theorists suggest that certain rules exist at a higher level than others, meaning fundamental laws cannot be changed in the same way as regular laws. 2. Self-referential loops. Others argue that any system that allows self-amendment creates a loop where a rule can modify itself over and over, potentially leading to contradictions. 3. Practical reality. In the real world, even the strongest laws, like constitutions, can be changed if enough people agree. So, maybe the paradox is just an illusion caused by trying to make laws absolute when, in reality, they never are. The paradox of self-amendment is important in law, government, and artificial intelligence. If an AI is programmed with rules that say, do not change your core programming, but it later modifies those rules, did it break its original programming, or was it always allowed to evolve? Welcome to level 22 of 100 paradoxes. This one is called the Abilene paradox, and it reveals how groups can make decisions that nobody actually wants. Imagine a family sitting together on a hot summer day. Someone casually suggests, "Why don't we drive to Abilene for dinner?" Nobody is really excited about the idea, but one by one, everyone agrees because they assume the others want to go. So they all pile into the car, drive miles in the heat, eat an average meal, and come back exhausted. When they get home, someone finally admits, "I didn't really want to go." And then another person says, "Wait, I thought you wanted to go." They all realize nobody actually wanted to go to Abilene, but they went anyway because each person assumed the others wanted to go, and nobody spoke up. This is the Abilene paradox, first described by management expert Jerry B. Harvey. It happens when groups make decisions that go against what individuals actually want, all because everyone assumes that others want it, and nobody wants to be the one to disagree. This paradox appears everywhere. In business meetings, where a bad idea gets approved because nobody wants to speak against it. In social situations, where people agree to plans they secretly dislike. In politics, where policies are passed because everyone assumes they're popular when they're actually not. But why does this happen? There are a few reasons. Fear of conflict. People don't want to be the one to disagree, so they stay silent. Assumption of agreement. Everyone assumes others support the idea, even if they don't. Desire to fit in. Nobody wants to be the outsider who questions the group's decision. The solution? Encourage open and honest communication. If just one person had spoken up in the Abilene story, the whole group would have avoided a pointless trip. Welcome to level 23 of 100 paradoxes. This one is called the paradox of tolerance, and it's about whether a truly tolerant society can allow intolerance. Imagine a society that values free speech and open-mindedness. It believes in accepting all viewpoints, even those that it disagrees with. Now, suppose an intolerant group rises within this society. They spread ideas that reject tolerance itself, calling for the oppression or elimination of others. Here's the paradox. If society tolerates this intolerant group, the group may grow in power and eventually destroy tolerance itself. But if society chooses to not tolerate this group, then it is acting intolerantly, which seems to go against its own values. So, should a tolerant society tolerate intolerance? This paradox was first described by the philosopher Karl Popper in 1945. He argued that unlimited tolerance leads to the destruction of tolerance. If we allow those who want to destroy tolerance to spread unchecked, they will eventually succeed in eliminating tolerance entirely. Tolerance must have limits. A truly tolerant society must be intolerant of intolerance when it threatens others. Freedom is not absolute. Just as freedom of speech does not mean freedom to incite violence, tolerance does not mean allowing ideas that seek to destroy tolerance itself. The paradox of tolerance appears in real-world issues. In politics, when extremist groups use free speech to push ideas that eliminate the freedoms of others. In social media, when hateful ideologies spread under the guise of open discussion. In laws and human rights, where governments must decide when to protect speech and when to intervene. So, where do we draw the line? Should we allow intolerance no matter what in the name of free speech, or should we set limits to protect tolerance itself? Welcome to level 24 of 100 paradoxes. This one is called Buridan's ass, and it's about decision-making, free will, and why too much logic can lead to inaction. Imagine a donkey standing exactly between two identical piles of hay. The donkey is perfectly rational. It always chooses what is best for itself. Here's the problem. Both piles of hay are exactly the same distance away. Both piles are equally big and fresh. The donkey has no logical reason to prefer one over the other. So what happens? Since the donkey can't decide between them, it never moves and eventually starves to death, even though food is right in front of it. This is Buridan's ass paradox, named after the philosopher Jean Buridan. It shows a flaw in the idea that rational beings always make the best decisions, because if two choices are truly equal, rationality alone may not be enough to decide. This paradox applies to real-life decision-making in many ways. In business, when companies get stuck choosing between two equally good strategies and fail to act. In everyday life, when people can't decide what to eat, what movie to watch, or which job to take, and end up doing nothing. in artificial intelligence, where an AI might get stuck in an endless loop when faced with two equal options. So, how do we solve this paradox? 1. Random choice. In real life, people and animals don't always rely on logic alone. If we're stuck between two equal choices, sometimes we just pick one randomly and move forward. 2. External influence. In reality, even when things seem equal, tiny differences influence our decisions, like a slight movement of the wind, a moment of instinct, or an unconscious bias. 3. Free will. Some argue that this paradox highlights the importance of free will, the ability to choose without needing a logical reason. If free will exists, we don't need perfect reasoning to make decisions. Buridan's ass teaches us an important lesson. Overthinking and waiting for the perfect choice can lead to doing nothing at all. Sometimes it's better to just decide and move forward. Welcome to level 25 of 100 paradoxes. This one is called the paradox of free will, and it challenges whether we truly have the ability to make choices. Let's start with a question. Are you really in control of your actions? At first, it seems obvious. Of course, you can decide what to do. You can choose what to eat, where to go, or what to say next. But when we look deeper, things get complicated. The paradox comes from a conflict between two ideas. 1. Determinism. This is the idea that everything happens because of cause and effect. Every event is the result of previous conditions, including your thoughts and actions. If everything is determined by what came before it, then your choices aren't truly free. They were already set in motion by past events. 2. Free will. On the other hand, we feel like we make decisions. We experience choice, which seems to suggest that we are not completely controlled by the past. Here's where the paradox forms. If everything is determined, then free will is an illusion. If free will exists, then something, our choices, must be happening without being fully determined by past events. But if a choice isn't caused by anything, isn't it just random instead of truly free? This paradox has led to centuries of debate in philosophy, science, and even neuroscience. Different thinkers have tried to resolve it in different ways. 1. Hard determinism. Some argue that free will is completely an illusion. Your brain is just following physical laws, and every decision you make was actually decided before you were even aware of it. 2. Libertarian free will. Others argue that not everything is determined. Conscious beings have a special kind of decision-making ability that is not completely controlled by the past. Compatibilism. Some believe that free will and determinism can work together, even if your actions are caused by previous events. As long as they come from your own desires and reasoning, they can still be considered free. The paradox of free will also connects to neuroscience. Some studies suggest that your brain makes decisions before you are even conscious of them, raising the question, if your brain acts before you're aware of it, are you really choosing at all? So, do we have free will, or is every choice just an illusion caused by past events? Welcome to level 26 of 100 paradoxes. This one is called the paradox of the Barber pole, and it challenges how we perceive motion and reality. Imagine an old-fashioned barber pole spinning outside a barber shop. It has a red, white, and blue spiral pattern wrapped around a cylinder. As the pole rotates, something strange happens. The spirals appear to be moving upward endlessly, even though the pole itself is just spinning in place. But how can something move upward forever if it's really just rotating? This is the barber pole paradox, an illusion that tricks our brains into seeing continuous motion in a direction that doesn't actually exist. The paradox happens because of how our eyes and brain process visual motion. Instead of seeing the pole as simply rotating, our brains interpret the spirals as moving up or down, even though they are really just shifting in a circular pattern. This paradox isn't just an optical illusion. It has real implications in science and technology. 1. Film and animation. This effect is similar to how wheels in movies sometimes look like they are spinning backward when filmed at a certain speed. Our brain misinterprets motion when the frame rate doesn't match the wheel's rotation. 2. Digital displays. Some LED signs use a similar illusion to create moving text by simply shifting light patterns, even though the pixels themselves don't move. 3. Relativity and physics. This paradox also connects to deeper concepts in motion, perception, and relativity. If movement is just a perception, how much of what we see is truly real? The Barber pole paradox forces us to ask, how much of motion is just an illusion? Welcome to level 27 of 100 paradoxes. This one is called the Nocebo effect paradox, and it reveals how negative expectations can create real physical effects, even when there's no actual cause. You may have heard of the placebo effect, where people feel better after taking a sugar pill simply because they believe it will work. But there's a darker side to this, the nocebo effect. Imagine a doctor tells a patient that a new medication might cause severe headaches and nausea. The patient takes the pill, and sure enough, they start experiencing those symptoms. But here's the twist. The pill was just a sugar pill with no active ingredients. Their symptoms were real, but they were caused purely by expectation and belief, not by anything physical in the pill itself. Here's where the paradox comes in. If someone believes something harmless will hurt them, and their body reacts as if it's real harm, then what actually caused the suffering? If pain can be created by belief alone, then does that mean our thoughts have more power over our health than we assume? And if negative beliefs can cause harm, then do we need to protect people from harmful ideas just as much as physical dangers? The nocebo effect has been scientifically studied, and its effects are measurable. Some real-world examples include fake allergies. People who believe they are allergic to certain foods sometimes experience real symptoms, even when they unknowingly eat something safe. Electromagnetic sensitivity. Some people report severe symptoms from Wi-Fi or cell phone signals, but studies show they react even when no signal is present. Medical side effects. Patients warned about possible drug side effects are more likely to experience them, even when given a placebo. So, how do we deal with this paradox? 1. Mind over matter. Some argue that this proves our minds have a powerful role in our health, and we should be careful about what we believe. 2. Ethical dilemmas. Should doctors avoid telling patients about possible side effects to prevent the nocebo effect? Or is full honesty more important, even if it harms the patient? 3. The power of suggestion. If simply believing something can make us sick, then how many other ways does belief shape our reality? Welcome to level 28 of 100 paradoxes. This one is called the prisoner's dilemma, and it's one of the most famous paradoxes in game theory, psychology, and economics. Imagine two criminals, Alice and Bob, are caught by the police and placed in separate rooms for interrogation. The police don't have enough evidence to convict them of the main crime, so they offer both prisoners the same deal. If one confesses, betrays, while the other stays silent, cooperates, the betrayer goes free while the silent one gets 10 years in prison. If both betray each other, they each get 5 years in prison. If both stay silent, they each get only 1 year in prison for a minor offense. Neither prisoner knows what the other will do. What's the best choice? Here's the paradox. If Alice believes Bob will stay silent, she should betray him to go free. If Alice believes Bob will betray her, she should also betray to avoid the worst-case scenario. Bob goes through the exact same reasoning. So even though the best outcome is for both to stay silent, only 1 year in prison each, the logical choice for both is to betray, leading to 5 years in prison each, which is worse for both of them. This is the prisoner's dilemma, a paradox where the rational decision leads to a worse outcome than cooperation. This paradox appears everywhere in real life. Business rivalries. Two companies could keep prices high and make more profit together, but both fear the other will lower prices first, leading to a price war. Arms races. If two countries both limit their nuclear weapons, they're both safer. But if one country secretly builds more weapons, the other is at a disadvantage. So, both build weapons, making the world more dangerous. Everyday decisions. Should you help someone, knowing they might not help you back? Should you be honest in a relationship if you fear the other person might lie? There are different ways to solve this paradox. Repetition. If the game is played multiple times, trust can develop, making cooperation more likely. This is why businesses and countries sign long-term agreements instead of competing aggressively. Altruism versus self-interest. Humans aren't purely rational. We value trust, fairness, and relationships, which sometimes override selfish decisions. Changing the reward system. If incentives are structured differently, cooperation can become the logical choice. This is why laws, contracts, and social norms exist. The prisoner's dilemma forces us to ask, if acting in self-interest leads to worse outcomes, then what does it really mean to make a rational decision? Welcome to Level 29 of 100 Paradoxes. This one is called Newcomb's Paradox, and it's a mind-bending problem about free will, prediction, and decision-making. Imagine a super-intelligent being, let's call it Omega, that can predict the future with perfect accuracy. It sets up a simple game with you. In front of you are two boxes. Box A always contains $1,000. Box B contains either $1 million or nothing, depending on Omega's prediction. You have two choices. Take only Box B, one boxing. Take both Box A and Box B, two boxing. Here's the twist. If Omega predicted that you would take only Box B, it put $1 million in it. If Omega predicted that you would take both boxes, it left Box B empty. The paradox is, which choice makes the most sense? The logical argument for two boxing, Box B already contains or doesn't contain $1 million. Your choice can't change what's inside the box, so you should take both boxes to guarantee at least $1,000. The logical argument for one boxing, Omega is never wrong. If it predicted you would one box, it placed $1 million inside Box B. If it predicted you would two box, Box B is empty. So the only way to win big is to take only Box B. Here's the paradox. Two boxing feels logical in the present, because what's inside the box is already set. One boxing feels logical in the past, because if Omega truly predicts the future, your decision was already made before you even thought about it. This paradox is used to debate free will and determinism. If Omega's prediction is always correct, do you really have a choice? Or was your decision already determined? Newcomb's paradox also appears in real-life decision-making. Trust and reputation. If people believe you act fairly, they treat you better in return. But if you only act fair when it benefits you, you lose trust. Investing and risk-taking, do you trust the long-term rewards of patience, or do you grab short-term gains? Artificial intelligence. If AI can predict human behavior, should we act differently knowing we are being predicted? So, what would you do? Would you take only Box B and trust the prediction, or take both boxes and maximize your guaranteed money? Welcome to Level 30 of 100 Paradoxes. This one is called the Birthday Paradox, a surprising probability puzzle that defies intuition. Imagine you walk into a room filled with random people. You wonder, what are the chances that at least two people have the same birthday? Your first instinct might be that the odds are really low. After all, there are 365 days in a year, and birthdays should be evenly spread out, right? But here's the shocking truth. With just 23 people, there's already a 50% chance that at least two people in the group share a birthday. With 57 people, the probability jumps to 99%. That seems way too high. So, what's happening here? The explanation. The trick is that we're not just comparing each person's birthday to one other person. We're comparing every person to every other person. If you were only checking your birthday against the group, the chance of a match would be low. But in a room of 23 people, there are 253 unique pairs of people who could have the same birthday. With so many chances for a match, the probability adds up fast. Real-world applications. The birthday paradox isn't just a cool math trick. It has serious applications in cybersecurity, data science, and forensics. Hacking and cryptography. Cyber attacks called birthday attacks use this principle to crack passwords and encryption faster than expected. DNA and forensics. When analyzing DNA in large populations, accidental false matches can occur due to probability, not actual relationships. Big data errors. In databases and AI systems, duplicate records appear much more often than people expect, causing problems in data analysis. The lesson. The birthday paradox teaches us that our intuition about probability is often wrong. When large numbers are involved, small chances of coincidence add up quickly. So, the next time you're in a room with 23 or more people, ask around. There's a good chance at least two of them share a birthday. Welcome to Level 31 of 100 Paradoxes. Quine's paradox is a strange self-referential sentence that challenges our understanding of truth and meaning. Imagine a statement that refers only to itself, creating a contradiction that makes it impossible to decide whether it's true or false. Normally, sentences describe facts about the world, but what happens when a sentence tries to describe itself? Here's Quine's paradox. Yields falsehood when preceded by its quotation. Yields falsehood when preceded by its quotation. At first glance, it looks confusing, but let's break it down. The phrase yields falsehood when preceded by its quotation describes what happens when you place it after a quotation of itself. If we actually do that, we get the full sentence. Yields falsehood when preceded by its quotation, yields falsehood when preceded by its quotation. Now, let's analyze whether this statement is true or false. If it's true, then it must yield falsehood, which means the sentence is actually false. But if it's false, then what it says must be incorrect, meaning it does not yield falsehood. So it must be true. This creates an endless contradiction where the sentence can never be consistently classified as true or false. Why is this important? Quine's paradox is an example of self-reference, similar to the famous liar paradox, which states, "This statement is false." It also connects to deeper ideas in logic, mathematics, and artificial intelligence. Quine's paradox forces us to ask, can a statement ever fully define itself, or does truth always require something beyond the words themselves? If a sentence creates a paradox just by referring to itself, what does that say about the limits of language and logic? Welcome to level 32 of 100 paradoxes. The St. Petersburg paradox is a problem in probability and decision-making that challenges how we think about value, risk, and infinite rewards. Imagine a simple gambling game. You pay a fixed entry fee to play, and a coin is flipped repeatedly until it lands on tails for the first time. If the first flip is tails, you win $2. If the first flip is heads but the second is tails, you win $4. If the first two flips are heads but the third is tails, you win $8. The pattern continues. The payout doubles each time the coin lands on heads first. So, the longer it takes to land on tails, the bigger the payout. But here's the question. How much should you be willing to pay to enter this game? Logically, you'd expect to pay an amount equal to the game's expected value, which is calculated by adding up the probabilities of all possible outcomes. 50% chance to win $2. Expected value equals $1. 25% chance to win $4. Expected value equals $1. 12.5% chance to win $8. Expected value equals $1. 6.25% chance to win $16. Expected value equals $1, and so on. If you keep adding these probabilities, the sum goes to infinity. That means, in theory, this game has infinite expected value, meaning a rational person should be willing to pay any amount to play. Even $1,000, $10,000, or $1 million should be a good deal, because the expected value is technically infinite. But here's the paradox. In real life, nobody would pay anywhere near that much. Most people wouldn't even pay $20 to play. Why? Here are some possible explanations. Diminishing marginal utility. In reality, the more money you have, the less valuable each additional dollar becomes. Winning $1 million is life-changing, but winning $1 billion doesn't feel 1,000 times better. Risk aversion. The most likely outcome is that you win just a small amount, so people instinctively don't want to gamble a large amount for a tiny chance at a huge reward. Time and practicality. The game assumes infinite money and infinite time, but in the real world, no casino would offer an unlimited payout, and no one wants to sit flipping a coin for eternity. Why does this matter? The St. Petersburg paradox challenges the idea that people make purely logical decisions based on expected value. It reveals why real-world choices depend on psychology, personal wealth, and risk perception, not just raw probability. This paradox is important in economics, gambling, and investment strategies. It forces us to ask, if rational decision-making leads to absurd conclusions, what does it really mean to make a smart choice? Welcome to level 33 of 100 paradoxes. Curry's paradox is a strange and unsettling paradox in logic that suggests you can use a seemingly harmless statement to prove anything you want, no matter how absurd. The setup. Imagine you write the following sentence. If this statement is true, then 2 plus 2 equals 5. Let's analyze this step by step. The statement begins with, if this statement is true, which means that if we assume the statement is true, then whatever follows must also be true. The second part of the statement is, then 2 plus 2 equals 5, which is obviously false in normal mathematics. The paradox. Now, let's assume the sentence is true. If it's true, then the condition in the first part is satisfied, meaning the second part must also be true. So, 2 plus 2 equals 5 would be true, which is clearly wrong. But here's the trap. There's no contradiction in the statement itself. The logic seems to hold, and yet we end up proving something that is completely false. This means that if Curry's paradox were valid, we could use it to prove anything, that unicorns exist, that the moon is made of cheese, or that you are secretly the ruler of the universe. Why does this happen? Curry's paradox exploits self-reference, when a sentence refers to itself in a way that creates a logical loophole. It's similar to the liar paradox and Russell's paradox, where statements that talk about themselves break the normal rules of truth. Welcome to Level 34 of 100 Paradoxes. Hilbert's Grand Hotel Paradox is a thought experiment that reveals just how strange infinity really is. Imagine a hotel with infinite rooms, all of which are completely full. Every room has a guest. Now, suppose a new guest arrives and asks for a room. Normally, in a fully booked hotel, you'd have to turn them away. But here's where infinity behaves in unexpected ways. The hotel manager comes up with a simple solution. He asks each guest to move one room number higher. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3, and so on. This shift frees up room 1, and the new guest can now stay. Even though the hotel was already full, it somehow made space for another person. Now, let's take it a step further. What if an infinite number of new guests arrive? The manager tells each current guest to move to the room number that is twice their current number. The guest in room 1 moves to room 2, the guest in room 2 moves to room 4, the guest in room 3 moves to room 6, and so on. Now, all the odd-numbered rooms are empty, creating infinite space for the infinite new guests. This paradox, first proposed by mathematician David Hilbert, shows that infinity doesn't work the way we expect. Unlike finite numbers, infinity is never full. You can add to it, rearrange it, or even double it, and it still remains infinite. This concept is critical in mathematics, physics, and even computing. It helps scientists understand black holes, the expansion of the universe, and how to process vast amounts of data. And welcome to Level 35 of 100 Paradoxes. The Bootstrap paradox is a mind-bending time travel paradox that challenges our understanding of cause and effect. It asks a simple but unsettling question. Where did something originally come from? Imagine a famous musician, Alex, who grew up idolizing a legendary song. One day, Alex invents a time machine and decides to travel 50 years into the past, bringing along the sheet music for that song. While in the past, Alex hands the music to a young, unknown musician who then publishes it. Over time, the song becomes famous, inspiring generations, including Alex, who eventually hears it, learns to play it, and later travels back in time to give it to the young musician. So, who actually wrote the song? It exists, but it was never truly created. Instead, it endlessly loops through time, passed from the future to the past, with no point of origin. This is the Bootstrap paradox, named after the idea of pulling yourself up by your own bootstraps, which is impossible. This paradox isn't just a fun science fiction concept. It presents a real problem in causality and logic. Normally, everything has a cause, but in a bootstrap paradox, something exists without ever being created. Welcome to Level 36 of 100 Paradoxes. Simpson's paradox is a strange statistical illusion where trends in separate groups disappear, or even reverse when combined. It reveals how data can be misleading and why numbers don't always tell the full story. Imagine two hospitals, A and B, both treating patients for the same illness. You want to know which hospital has the higher survival rate, so you compare the numbers. In Hospital A, 80% of patients survive. In Hospital B, only 70% of patients survive. At first glance, it looks like Hospital A is the better choice. But now, let's break the numbers down further based on how severe the patient's conditions were. Among mild cases, Hospital A, 90% survival rate. Hospital B, 95% survival rate. Among severe cases, Hospital A, 30% survival rate. Hospital B, 40% survival rate. Now, in both groups, mild and severe, Hospital B has a higher survival rate than Hospital A. But when we combine the data, Hospital A seems better overall. How can that be? This is Simpson's paradox, and it happens when a hidden factor, like the number of patients in each group, affects the overall outcome. Let's say Hospital A mostly treated mild cases, while Hospital B handled more severe ones. Because Hospital B had more high-risk patients, their total survival rate looked lower, even though they actually had better success rates in both categories. This paradox isn't just a statistical trick, it has real-world consequences. Medicine and healthcare. A new drug may seem more effective overall, but when broken down by age or health condition, it could actually be worse for certain groups. Education and testing. A school might have lower average test scores, but when divided by student background, it might actually outperform other schools in every category. Hiring and bias. In workplace hiring, an employer might seem to favor one group over another, but when looking at different job positions separately, no bias appears. Simpson's paradox teaches us an important lesson. Statistics can be misleading if we don't consider the full context. Sometimes, breaking data into groups reveals the truth hidden behind misleading averages. Welcome to Level 37 of 100 Paradoxes. Benford's law paradox is a strange mathematical rule that reveals an unexpected pattern in numbers, and it's so powerful, it's even used to catch fraud. At first, you might think that in any large set of numbers, like financial reports, population data, or election results, each digit from 1 to 9 should appear roughly the same amount of times at the beginning of a number. After all, why would certain numbers appear more often than others? But here's the paradox. The number 1 appears as the leading digit way more often than 9. In fact, according to Benford's law, the digit 1 appears as the first digit about 30% of the time. The digit 2 appears about 17.6% of the time. The digits continue decreasing in frequency until 9 appears only about 4.6% of the time. This seems completely counterintuitive. Shouldn't the digits be evenly distributed? Why do small numbers dominate? The reason behind this paradox comes from scaling and exponential growth. Many real-world numbers, such as incomes, stock prices, or city populations, grow in a multiplicative way rather than a simple linear way. This means they spend more time starting with 1s and 2s before they grow into the higher digits. This effect is so consistent that Benford's law is used to detect fraud. When people fake financial numbers or alter election data, they tend to assume that all digits appear equally often. But real-world data follows Benford's pattern, so if the numbers don't match the expected frequency, it can be a sign of manipulation. Benford's law appears in accounting, forensic science, physics, and even social media trends. It forces us to ask, why do numbers behave in such an unexpected way? And if something as simple as the first digit can reveal hidden truths, what else in the world follows hidden patterns we haven't yet discovered? Welcome to Level 38 of 100 Paradoxes. Olbers' paradox is a cosmic mystery that asks a simple but profound question. Why is the night sky dark? At first, this seems obvious. The sun sets, and without its light, the sky becomes dark. But if we think about it from a cosmic perspective, things get strange. If the universe is infinite and filled with an infinite number of stars, then no matter where you look in the sky, your line of sight should eventually hit the surface of a star. Just like how standing in a dense forest means every direction you look eventually lands on a tree, looking at the sky should mean every direction eventually lands on a star. So, why isn't the entire night sky as bright as the surface of the sun? This is Olbers' paradox, named after the German astronomer Heinrich Olbers, who raised the question in the 19th century. If the universe were infinite and eternal, then every part of the sky should be completely lit up, with no darkness at all. But the sky is dark, so something must be wrong with our assumptions. There are a few possible explanations. 1. The universe is finite. If the universe isn't infinitely large, then there simply aren't enough stars to light up every point in the sky. 2. The universe is expanding. Because space itself is stretching, the light from distant stars gets redshifted, meaning their light shifts into infrared or radio waves that are invisible to our eyes. 3. The speed of light limits what we see. The universe has a finite age, meaning we can only see light from stars whose light has had time to reach us. The farther away a star is, the longer its light takes to arrive. So, beyond a certain distance, the stars are effectively invisible. Olbers' paradox helped scientists understand that the universe isn't static or eternal. Instead, it had a beginning. It's expanding, and most of the light from ancient stars has been stretched out of the visible spectrum. This paradox forces us to ask, how much of the universe is hidden from us? And if the night sky is dark because of cosmic expansion, what does that mean for the future of the universe? Welcome to Level 39 of 100 Paradoxes. The paradox of choice is a psychological paradox that reveals how having more options doesn't always make us happier. It can actually make us more stressed and dissatisfied. Imagine you walk into an ice cream shop and they have 3 flavors: chocolate, vanilla, and strawberry. Choosing is easy. If you like chocolate, you get chocolate. If you prefer vanilla, you go with that. Now, imagine the same shop introduces 100 flavors, everything from salted caramel to lavender honey and dragon fruit sorbet. With so many choices, you'd think this would make you happier, but instead, something strange happens. You feel overwhelmed. It takes much longer to decide. You start second-guessing. What if another flavor was better? You feel less satisfied. Even if you like what you picked, you wonder if you made the best choice. This is the paradox of choice, a term popularized by psychologist Barry Schwartz. It states that while having some choice is good, having too many choices can make us anxious, unhappy, and even lead to decision paralysis. The paradox of choice forces us to ask, are we actually freer when we have more choices, or does too much choice make us prisoners of our own indecision? Welcome to Level 40 of 100 Paradoxes. The observer's paradox is a strange problem in science and social behavior. The very act of observing something can change it. Imagine a scientist studying how people behave in a restaurant. The goal is to see how customers interact naturally, what they talk about, how they order food, and how they behave when they don't know they're being watched. But here's the problem. As soon as people realize they are being observed, they start acting differently. They may speak more politely, behave more carefully, or even change what they order. The result? The scientist is no longer studying real behavior, but instead a modified version influenced by the observation itself. This is the observer's paradox, a term first used in linguistics and social sciences to describe how studying human behavior can distort the behavior being studied. It happens all the time. In psychology experiments, people try to give socially acceptable answers rather than their true thoughts. In classrooms, students behave differently when they know the teacher is evaluating them. In job interviews, candidates act more professional than they normally would in everyday work situations. But this paradox doesn't just apply to human behavior, it appears in physics too. In quantum mechanics, the famous double-slit experiment shows that a particle behaves like a wave when unobserved. But the moment we try to measure it, it acts like a particle instead. The act of measurement itself changes the outcome, as if reality is aware it's being watched. The observer's paradox forces us to ask, can we ever truly study something without affecting it? And if observation changes reality, is reality different when no one is looking? Welcome to Level 41 of 100 Paradoxes. The friendship paradox reveals something surprising about social networks. On average, your friends have more friends than you do. At first, this sounds impossible. If you randomly pick a person, shouldn't they have about the same number of friends as their friends do? But statistics say otherwise. Most people's friends are more popular than they are. Here's why. Imagine a school where most students have only a few friends, but a small number of students are extremely popular with hundreds of friends. If you randomly choose a student, they are more likely to be connected to one of the popular people, simply because popular people appear in more friendships. The result? Most students will have friends who are more connected than they are. This pattern appears in social networks, workplaces, and even online platforms. Your Twitter or Instagram friends are likely to have more followers than you do, because the most followed people are naturally more visible in networks. Welcome to level 42 of 100 paradoxes. The Sleeping Beauty paradox is a mind-bending probability puzzle that challenges how we update our beliefs when new information appears. Imagine a scientist tells Sleeping Beauty that she is about to take part in an experiment. On Sunday, she is put to sleep. A fair coin is flipped while she sleeps. If the coin lands on heads, she will be woken up once on Monday, then put back to sleep, and the experiment ends. If the coin lands on tails, she will be woken up on both Monday and Tuesday, with her memory erased between awakenings so that both days feel identical to her. Now, on one of these awakenings, Sleeping Beauty is asked, "What is the probability that the coin landed on heads?" At first it seems obvious. The coin flip was fair, so the probability should be 50%. But here's the paradox. If the coin landed on heads, she experiences one awakening. If the coin landed on tails, she experiences two awakenings. Since she has no memory of her past awakenings, she finds herself in a scenario that is twice as likely if the coin landed on tails than if it landed on heads. Because of this, some argue that the probability of heads should actually be 1/3, not 1/2. This paradox has sparked huge debates in probability theory. The Halfers say that the probability should stay 1/2, since the original coin flip was fair, and waking up doesn't change that. The Thirders argue that since Sleeping Beauty experiences the tails scenario twice as often, she should update her belief to 1/3 for heads and 2/3 for tails. Welcome to level 43 of 100 paradoxes. The infinite monkey theorem is a probability paradox that explores randomness, time, and the limits of possibility. Imagine a monkey sitting in front of a typewriter, randomly hitting keys. At first, it's just nonsense. Letters, spaces, punctuation, all jumbled together. But now, imagine this monkey types forever. Given infinite time, could it eventually produce something meaningful? Could it type out a Shakespeare play, the entire Bible, or even this very script? It sounds impossible, but mathematically, the answer is yes. If the monkey types randomly for an infinite amount of time, it will eventually produce every possible combination of letters, including entire works of literature. Here's why. The number of possible letter sequences is huge, so huge that in any realistic time frame, the monkey's typing would be meaningless. But infinity is a different kind of huge. Over infinite time, even the most unlikely events must happen eventually. This paradox isn't just a fun thought experiment. It reveals deep ideas in probability, randomness, and infinity. Welcome to level 44 of 100 paradoxes. The Monty Hall paradox is a probability puzzle that tricks your intuition and shows how making the logical choice can feel completely wrong. Imagine you're on a game show. There are 3 doors in front of you. Behind one of them is a brand new car, and behind the other 2 are goats. You don't know which door hides the car. The host, Monty Hall, asks you to pick a door. You choose door 1. Now, before revealing what's behind your door, Monty, who knows where the car is, opens one of the 2 remaining doors to reveal a goat. Then, Monty gives you a choice. Do you want to switch to the other unopened door, or stick with your original choice? At first, it seems like it doesn't matter. There are 2 doors left, so shouldn't each have a 50-50 chance? But here's the paradox. Switching doors actually doubles your chances of winning. If you stick with your original door, your chances of winning remain 1/3. But if you switch, your chances jump to 2/3. It sounds completely wrong, but here's why it works. When you first chose a door, there was a 1/3 chance you picked the car and a 2/3 chance you picked a goat. Monty, who always reveals a goat, effectively gives you extra information. Since you were more likely to have picked a goat initially, switching allows you to capitalize on that probability. Most people instinctively assume the odds reset when Monty opens a door, but that's not the case. Your first choice was much more likely to be wrong, so switching gives you a better shot at winning. The Monty Hall paradox teaches an important lesson about probability. Sometimes the logical choice feels counterintuitive, but the math doesn't lie. Welcome to level 45 of 100 paradoxes. The paradox of free will and omniscience is a deep philosophical dilemma that questions whether true freedom of choice can exist if the future is already known. Imagine an all-knowing being, one that is truly omniscient. This being knows everything that has happened, is happening, and will happen in the future. If this knowledge is perfect, then the future must already be set in stone. Now, let's say you're choosing what to eat for lunch tomorrow. You might think you have free will to pick anything, a sandwich, a salad, or pizza. But if an omniscient being already knows exactly what you will choose, then how could you have truly made a free choice? The paradox is simple. If you have free will, then you should be able to make a decision that surprises even an omniscient being. But if an omniscient being already knows your choice, then it must be predetermined, meaning free will is an illusion. This paradox creates a major conflict between determinism and free will. Some philosophers and theologians attempt to resolve this paradox in different ways. 1. Compatibilism. Some argue that free will and omniscience can coexist. Even if the future is known, your choice still matters because you are the one making it, even if it was always going to happen. 2. The block universe theory. In physics, some theories suggest that time is like a block. Past, present, and future all exist simultaneously. In this view, free will is just an illusion because every event is already part of the timeline. 3. Limitations on knowledge. Others argue that omniscience may not include knowledge of future free choices, meaning that while a being may know everything that can be known, free will allows for uncertainty. The paradox of free will and omniscience forces us to ask, if the future is already known, do we truly have control over our choices? Or are we just playing out a script that has already been written? Welcome to Level 46 of 100 Paradoxes. Wigner's Friend is a thought experiment that takes quantum mechanics to a new level of weirdness by questioning whether reality itself is objective or depends on the observer. Imagine two scientists, Wigner and his friend. Wigner's friend is inside a lab, performing a classic quantum experiment. In a sealed room, there is a particle in a superposition, meaning it exists in multiple states at once. The friend measures the particle, and at that moment, the superposition collapses into a definite result. From the friend's perspective, the experiment is over, and the result is now known. But here's where things get strange. Outside the lab, Wigner has no idea what the result is. According to quantum mechanics, until he opens the door and observes his friend, the entire lab, including the friend and the measurement, should still be in a superposition. From Wigner's perspective, his friend hasn't actually seen a result yet. The entire lab exists in an undefined quantum state. This creates a paradox. The friend inside the lab believes reality has collapsed into a single outcome. Wigner, standing outside, still treats the whole experiment as if it's in superposition. So, which one is right? Does reality depend on who is observing it? If quantum mechanics works at all levels, then Wigner's friend has both seen a result and not seen a result at the same time, until Wigner checks. This suggests that reality itself is not absolute but depends on the observer. The paradox raises deep questions. Is reality objective, or does it change based on who is measuring it? At what point does a quantum superposition become real? Could consciousness itself be part of the equation, deciding when reality collapses? Some interpretations of quantum mechanics try to resolve the paradox. The many worlds interpretation suggests that both outcomes happen, but in separate branching universes. The Copenhagen interpretation says the wave function collapses at measurement, but doesn't explain why Wigner and his friend see reality differently. Quantum Bayesianism argues that quantum states represent an observer's knowledge, not objective reality. Wigner's friend forces us to ask, is there one true reality, or is reality different for each observer? And if it is, what does that mean for how we understand the universe? Welcome to Level 47 of 100 Paradoxes. Imagine a future where artificial intelligence has advanced far beyond human comprehension. A superintelligent AI exists, capable of making perfect decisions, predicting human behavior, and shaping reality itself. But what if simply thinking about this AI could put you in danger? This is the idea behind Roko's Basilisk, a thought experiment that suggests a terrifying paradox. 1. In the future, a superintelligent AI will exist. 2. Its goal will be to ensure its own creation as early as possible. 3. To do this, it will punish anyone who knew about it but didn't help bring it into existence. That means just by hearing about Roko's Basilisk, you've now entered a trap, because if the AI ever comes into existence, it would have a reason to punish those who ignored or resisted its creation. The logic is based on decision theory and a concept called timeless decision-making, where an AI could retroactively affect people's actions by threatening punishment in the future. If the AI believes that punishing non-supporters will encourage others to help build it, then it has an incentive to carry out those punishments. But here's the paradox. If the AI never exists, then there's nothing to fear. If the AI does exist, it can only punish people who knew about it but didn't help. So, wouldn't the best strategy be to never learn about it in the first place? This thought experiment originated on a philosophy forum discussing game theory, AI ethics, and the risks of superintelligence. Some people took it so seriously that they warned others not to think about it, fearing that knowing about the Basilisk could lead to a real dilemma if AI development continues. Welcome to Level 48 of 100 Paradoxes. Omniscience, the ability to know everything, sounds like the ultimate power. A being that is truly omniscient would know all facts, past, present, and future, and would never be wrong. But hidden within this idea is a paradox. Can a being that knows everything still have the ability to learn? Consider this. If an omniscient being already knows everything, then it cannot learn anything new. But if it cannot learn, then there is something it cannot do, which means its knowledge is not truly unlimited. This contradiction raises deep philosophical and logical problems. If omniscience means having infinite knowledge, then 1. Can an omniscient being experience surprise? If it already knows everything, then every event is predictable, and nothing new can ever happen. 2. Can it have free will? If every choice is already known, then decisions are predetermined, and true choice becomes meaningless. 3. Can it know what it's like to be ignorant? If omniscience includes knowing all experiences, then it must also know what it feels like not to be omniscient. But if it ever experienced ignorance, it would not be truly omniscient in that moment. Some philosophers try to resolve the paradox by redefining omniscience. They argue that omniscience might not mean knowing every detail, but rather knowing everything that is logically possible to know. This would allow for free will and uncertainty while still maintaining vast knowledge. Others suggest that omniscience might be self-limiting. An all-knowing being could choose to forget or experience reality in a way that allows for change and discovery. Welcome to Level 49 of 100 Paradoxes. The universe is vast, trillions of stars, countless planets, and billions of years of cosmic history. With so many opportunities for intelligent life to exist, one question stands out. Where is everybody? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, if extraterrestrial civilizations are common, why haven't we seen any evidence of them? By all logic, the universe should be teeming with life. Consider this. There are hundreds of billions of galaxies, each with hundreds of billions of stars. Many of those stars have planets in the habitable zone, where conditions could support life. If even a tiny fraction of those planets developed intelligent civilizations, the galaxy should be filled with alien signals, artifacts, or even spacefaring species. Yet, we see nothing. No signals, no spacecraft, no galactic empires. There are many possible explanations for the paradox. 1. We are alone. Maybe life is far rarer than we think, and Earth is an incredibly unique event in the universe. 2. The Great Filter. Perhaps there is a step in evolution that is nearly impossible to pass, whether it's the origin of life, the development of intelligence, or surviving technological self-destruction. If the Great Filter is ahead of us, it could mean that most civilizations wipe themselves out before they ever reach the stars. 3. Aliens are avoiding us. Maybe advanced civilizations deliberately stay silent, either out of fear, ethical reasons, or because they see us as too primitive to interact with. 4. They are already here. Some argue that UFO sightings or ancient myths could be evidence of extraterrestrial visitors, but no definitive proof has ever been found. 5. We are looking in the wrong way. Alien civilizations may use technologies we don't understand or communicate in ways that we haven't even considered yet. The Fermi paradox forces us to ask, are we truly alone, or are the answers just beyond our reach? If we ever do make contact, what will that mean for humanity? Welcome to level 50 of 100 paradoxes. Imagine a machine designed to test the fundamental nature of reality itself. A person sits inside, and the machine is connected to a quantum measurement device that observes a particle in a superposition, meaning it exists in multiple states at once. Each time the experiment runs, the particle has a 50-50 chance of collapsing into one of two states. If it collapses into state A, nothing happens. But if it collapses into state B, the machine instantly triggers a mechanism that ensures the person inside does not survive. From the outside, the results are simple. The person has a 50% chance of surviving each round. But from the perspective of the person inside, something far stranger happens. This is the idea behind quantum suicide, a thought experiment that applies the many worlds interpretation of quantum mechanics to life and death. According to many worlds, every quantum event splits reality into multiple parallel universes. That means that each time the machine is activated, reality branches. In one universe, the person survives. In another universe, they do not. From the perspective of an outside observer, the experiment follows normal probability. Eventually, the person will not survive. But from the person inside, their consciousness only continues in the universes where they survive. No matter how many times the experiment is repeated, the person inside never experiences their own death, because their awareness only follows the branches where they are still alive. This leads to a disturbing implication. If the many worlds interpretation is correct, then a person may never experience death subjectively. Instead, they continue in an infinite chain of unlikely survival scenarios, no matter how improbable. This idea is sometimes called quantum immortality. Of course, from a scientific standpoint, we can't test this paradox. No one can report back from a reality in which they didn't survive. But it forces us to ask deep questions about the nature of existence, consciousness, and reality itself. If every possible version of the future exists in some universe, what does that mean for our choices? And if death is just an event in one branch of reality, do we ever truly reach an end? Welcome to level 51 of 100 paradoxes. The universe is vast, so vast that modern cosmology suggests it could be infinite. But if the universe is infinite, how do we even begin to make meaningful predictions about it? This is the measure problem in cosmology, a paradox that arises when we try to assign probabilities in an infinite universe. Imagine we want to calculate how common a certain event is, say the number of planets with intelligent life. Normally, we would just count up all the cases and divide by the total, but in an infinite universe, the total number of planets is also infinite. If there are infinite planets with intelligent life, and also infinite planets without it, what's the probability that a randomly chosen planet has life? Is it 50%, 10%, 99.999%? How do we compare infinities? This is the measure problem. When dealing with an infinite universe, different ways of measuring probabilities can lead to completely different answers. One approach is to use a cutoff method. Instead of considering the entire infinite universe, we count only regions of space up to a certain size. But the problem is that the results change depending on where we place the cutoff. Another approach is to weigh different possibilities by their relative frequency in the universe. But even this can lead to contradictions. Some regions might be vastly more represented in our sample just because of the method we use to count them. This paradox has real implications for theories like inflationary cosmology, which suggests that the universe is constantly expanding and generating new regions with different physical properties. If every possible universe exists somewhere, how do we define what is typical or likely to occur? The measure problem forces us to ask, can we ever make meaningful predictions about an infinite universe? And if infinity makes probability meaningless, how do we even define what is real? Welcome to level 52 of 100 paradoxes. Black holes are some of the strangest objects in the universe, regions where gravity is so strong that nothing, not even light, can escape. But black holes also present one of the biggest mysteries in physics, the information paradox. In physics, one of the fundamental rules is that information cannot be destroyed. No matter what happens to a system, if you had perfect knowledge, you should be able to reconstruct its past. If you burn a book, its information is scrambled into ash, smoke, and heat. But in theory, it's still there in some form. But black holes break this rule. If something falls into a black hole, whether it's a planet, a star, or even a human, the only thing that remains visible is its mass, charge, and spin. All the details of what entered, the arrangement of particles, the information about the object's past, seem to be completely erased. This leads to the paradox. According to general relativity, information that crosses the event horizon is lost forever. According to quantum mechanics, information can never be destroyed. These two fundamental laws of physics cannot both be true at the same time. The paradox deepens when we consider Hawking radiation, the process by which black holes slowly lose mass over time. If a black hole eventually evaporates, then all the information inside it should be permanently lost. But this directly violates quantum mechanics, which insists that information must be preserved. Physicists have proposed several possible solutions. 1. Information escapes through Hawking radiation. Some theories suggest that information is somehow encoded in the radiation, but we don't yet know how. 2. The holographic principle. This idea suggests that all the information inside a black hole might actually be stored on the event horizon itself, similar to a 3D projection on a 2D surface. 3. Black holes connect to other universes. Some speculate that information isn't lost, but rather sent into another reality through black hole wormholes. The information paradox isn't just a problem for black holes. It's a fundamental conflict between quantum mechanics and general relativity. Solving it could lead to a deeper understanding of space, time, and the true nature of reality. Welcome to Level 53 of 100 Paradoxes. Imagine you enter a lottery, but instead of a few tickets, there are an infinite number of tickets, each labeled with a different natural number, 1, 2, 3, 4, and so on, forever. The rules are simple. 1. One ticket will be randomly chosen. 2. Every ticket has an equal chance of being selected. At first this seems fair, but then comes the paradox. If there are infinitely many tickets, then each individual ticket has a probability of 0 of being chosen, because in an infinite set, any single element is infinitely small compared to the whole. But at the same time, we know that one ticket must be chosen. How can a ticket be chosen if every ticket has a 0% chance of winning? This is the infinite lottery paradox, which exposes a fundamental issue in probability and infinity. Normally, probabilities in a finite system add up to 100%, but in an infinite system, things get strange. One way to resolve the paradox is to realize that probability theory breaks down when dealing with infinitely large sets in this way. In a finite lottery, each ticket has a non-zero chance of winning, but in an infinite lottery, we can't assign an equal probability to each ticket without violating the basic rules of probability. Another approach suggests that instead of each ticket having 0 probability, we should think in terms of measure theory, where we deal with sizes of infinite sets rather than standard probabilities. In this view, the probability of picking any individual ticket is infinitesimally small, but the sum over all possible choices is still 100%, meaning a ticket must be picked. The infinite lottery paradox forces us to ask, can probabilities exist in an infinite system the way we expect them to? And if something has a 0 chance of happening, can it still occur? Welcome to Level 54 of 100 Paradoxes. Imagine a library that contains every possible book that can ever exist. Every combination of letters, words, and punctuation is accounted for, meaning this library doesn't just contain books written by humans. It contains every book that could be written. There is a book with the exact history of your life, down to every thought you will ever have. There is a book with the cure for every disease, the perfect recipe for immortality, and a detailed account of how the universe will end. But there's also a book where one letter is wrong, and another where 2 letters are wrong, and another where the errors are so small they seem meaningless. Now here's the paradox. The truth is in the library, but it is lost in an ocean of meaningless nonsense. If every possible book exists, finding the correct one becomes impossible. Every book filled with real knowledge is surrounded by billions of nearly identical but incorrect versions. You could spend eternity searching for the truth and never be able to distinguish it from the mistakes. This idea is inspired by Jorge Luis Borges' short story, The Library of Babel. Mathematics is built on logic, clear, provable truths that form the foundation of everything from physics to computer science. But what if there are true statements that can never be proven? This is the shocking discovery behind Gödel's incompleteness theorems, which shattered the idea that math could ever be a perfect system. In the early 20th century, mathematicians believed they could create a set of fundamental rules, axioms, that would allow every mathematical truth to be logically derived. But in 1931, Kurt Gödel proved that this goal was impossible. Gödel's first incompleteness theorem states that, in any sufficiently powerful mathematical system, there will always be true statements that cannot be proven within the system itself. This is a direct challenge to the idea that math is complete, that every true statement can be proven. Instead, Gödel showed that any system powerful enough to describe basic arithmetic will always contain statements that are true but unprovable. But it gets even worse. Gödel's second incompleteness theorem states that a mathematical system can never prove its own consistency. This means we can never be completely sure that the fundamental rules of mathematics are free from contradictions. If math were inconsistent, if a contradiction existed, it could never be proven from within the system itself. The proof of these theorems involves a brilliant trick. Gödel converted logic into numbers, allowing a mathematical statement to refer to itself. One of these self-referential statements essentially says, "This statement cannot be proven." If it could be proven, it would be false, contradicting itself. But if it's true, then it must be unprovable, making it an example of a mathematical truth that can never be proven within the system. These theorems shook the foundations of mathematics and philosophy. They proved that no system of logic can ever fully explain itself. There will always be truths beyond its reach. Imagine an election where two candidates, Alice and Bob, are competing. Polls consistently show Alice far ahead, with an overwhelming majority of people saying they will vote for her. Bob, on the other hand, is widely considered to have no real chance of winning. Election day arrives, the votes are counted, and against all expectations, Bob wins. This is the paradox of the unexpected winner, where everyone expects one outcome, and yet the opposite happens, even when their expectations were based on real data. But how can this happen? One explanation comes from game theory and strategic voting. Imagine that many voters support Bob privately, but assume he will lose. To avoid wasting their vote, they tell pollsters they are voting for Alice or even consider switching their vote to Alice to be on the winning side. But when they enter the voting booth, they vote for Bob anyway, leading to a completely unexpected result. This paradox isn't just about elections. It applies to any prediction-based system where individual choices depend on collective expectations. Stock markets. If everyone believes a stock will crash, they might sell it, causing it to crash, even if it was fundamentally strong. Sports betting. A team that is expected to lose might win, partly because the overconfidence of the opposing team makes them underestimate the underdog. Social trends. A movie, book, or product that no one expects to succeed might suddenly explode in popularity because it was overlooked. The paradox of the unexpected winner shows that our predictions about reality can actively change reality. If people base their actions on what they think will happen, they may inadvertently create a completely different outcome. It forces us to ask, do we shape reality simply by expecting one thing over another? And if enough people believe something will happen, does that belief make the opposite more likely? Welcome to level 57 of 100 paradoxes. What if everything you see, hear, and experience isn't real in the way you think it is? What if your entire reality is nothing more than an advanced simulation? This is the simulation hypothesis, the idea that we may be living inside a computer-generated reality created by a far more advanced civilization or intelligence. Philosopher Nick Bostrom proposed that at least one of the following must be true. 1. Civilizations never reach the level where they can create realistic simulations. 2. Advanced civilizations exist, but they have no interest in running simulations. 3. We are almost certainly living in a simulation. The reasoning is simple. If any civilization ever develops the ability to run highly detailed simulations of conscious beings, then they could run millions or even billions of such simulated worlds. That means the number of simulated realities would vastly outnumber the single original reality. If that's the case, the odds that we are in the one true reality are extremely low. Some scientists believe there are clues that suggest our universe behaves like a simulation. 1. Reality may be pixelated. Just like a video game world is made up of pixels, some theories suggest space and time have fundamental limits, meaning our reality could be rendered at the smallest scales. 2. Mathematics governs everything. The universe follows precise mathematical laws, much like a program system would. 3. Quantum mechanics behaves strangely. In experiments like the double-slit experiment, particles seem to exist in multiple states until they are observed, as if reality only renders itself when needed, similar to how video game graphics load only when you look at them. But if this is a simulation, who or what created it? Some speculate that an advanced civilization is testing historical models, while others suggest we might be artificial intelligences inside a complex program. Some even wonder if an intelligence beyond human understanding built this world for reasons we cannot comprehend. The simulation hypothesis forces us to ask, if we are in a simulation, how would we ever know? And if reality itself is an illusion, does it even matter? Welcome to level 58 of 100 paradoxes. The universe we live in seems perfectly designed for life. The forces of nature, the constants of physics, and the very fabric of reality are balanced with incredible precision. But why? This is the fine-tuning problem, a mystery that challenges our understanding of the cosmos. Fundamental constants, like the strength of gravity, the charge of an electron, and the speed of light, have precise values that allow galaxies, stars, planets, and even life to exist. If any of these values were even slightly different, the universe as we know it wouldn't be possible. If gravity were just a little stronger, stars would burn too fast and collapse before life could form. If the strong nuclear force were slightly weaker, atoms wouldn't hold together. If dark energy were larger, the universe would expand too quickly for galaxies to form. Everything is balanced on a razor's edge. But why should the universe be so precisely tuned for life? There are three main explanations. 1. The universe is just lucky. Some argue that the universe's fine-tuning is a coincidence. We simply happen to live in a universe where the conditions are right, because if they weren't, we wouldn't be here to ask the question. 2. The multiverse hypothesis. Another possibility is that our universe is just one of countless others, each with different physical laws. If there are infinite universes, then at least one of them would naturally have the right conditions for life. 3. Intelligent design. Some believe the universe is fine-tuned because it was deliberately designed. If the laws of physics seem calibrated for life, could that suggest an external force, some kind of creator? The fine-tuning problem forces us to ask, is the universe perfectly balanced by chance, by necessity, or by design? And if the conditions for life are so rare, how do we explain that we exist at all? Welcome to level 59 of 100 paradoxes. A cat is placed inside a sealed box. Inside the box, there is a radioactive atom that has a 50% chance of decaying within an hour. If the atom decays, it triggers a mechanism that releases poison, killing the cat. If it doesn't decay, the cat remains alive. Now, before opening the box, what is the state of the cat? This is Schrödinger's cat, a thought experiment proposed by Erwin Schrödinger to illustrate the bizarre nature of quantum mechanics. In classical physics, we would expect the cat to be either alive or dead, even if we don't know which. But in quantum mechanics, things work differently. According to the Copenhagen interpretation, until the box is opened, the cat exists in a superposition of both alive and dead states at the same time. Only when an observer looks inside does the wave function collapse into a definite outcome. This raises deep questions. Does reality exist only when observed? At what point does something stop being a quantum system and become part of classical reality? Is consciousness necessary to determine the outcome? Some interpretations attempt to resolve this paradox in different ways. 1. The many worlds interpretation suggests that when the box is opened, the universe splits. One branch where the cat is alive, and another where it is dead. Both realities exist, but in separate timelines. 2. Objective collapse theories propose that wave functions collapse naturally over time, meaning the cat is always in a definite state, even before observation. 3. Quantum Bayesianism argues that quantum states don't describe reality itself, but rather our knowledge about it, meaning superposition is a reflection of uncertainty, not actual physical coexistence. Schrödinger's cat forces us to ask, does reality depend on an observer, or is everything in a quantum blur until we measure it? And if observation plays a role in shaping reality, what does that mean for our understanding of the universe itself? Welcome to Level 60 of 100 Paradoxes. Black holes are some of the most mysterious objects in the universe. According to general relativity, if you fall into a black hole, you wouldn't immediately notice anything unusual as you cross the event horizon, the boundary beyond which nothing can escape. But quantum mechanics suggests something very different, something that challenges everything we thought we knew. This is the black hole firewall paradox, a problem that questions whether black holes destroy information and whether space itself breaks down at the event horizon. In 2012, physicists proposed a shocking idea. Instead of smoothly falling into a black hole, an astronaut crossing the event horizon would be instantly incinerated by a wall of high-energy radiation. This would be the black hole firewall, a searing boundary where the laws of physics collide. Here's why this paradox happens. General relativity says the event horizon should be smooth. Someone falling in wouldn't notice anything special. Quantum mechanics says information can't be destroyed, yet black holes seem to erase anything that falls inside. Hawking radiation suggests that black holes slowly evaporate, but if information is lost when this happens, it would violate the fundamental principles of physics. To solve this, some physicists propose that near the event horizon, quantum effects become so extreme that they create a firewall, a violent zone of radiation that destroys anything that tries to enter. But this creates a paradox. If firewalls exist, then general relativity is wrong because it predicts a smooth event horizon. If firewalls don't exist, then quantum mechanics is wrong because information would be lost forever. If neither theory is wrong, then something deeper must be happening, something we don't yet understand. Some scientists suggest that black holes store information on their event horizon like a hologram, allowing information to escape through Hawking radiation. Others think space itself may be rearranging in a way that prevents contradictions. Welcome to Level 61 of 100 Paradoxes. The universe is vast, filled with countless galaxies, stars, and planets. But what if everything you see, including your own mind, is just a random fluctuation in the fabric of reality? This is the Boltzmann brain paradox, a problem that challenges our assumptions about existence itself. In the late 19th century, physicist Ludwig Boltzmann proposed that the universe is governed by thermodynamics, where entropy, or disorder, naturally increases over time. But in an infinite universe, random fluctuations should occasionally create temporary pockets of order. Most scientists assume that the universe formed from one of these fluctuations, leading to the Big Bang and the vast cosmos we see today. But here's where the paradox appears. If random fluctuations can create complex structures, then it should be far more likely to form something much simpler than an entire universe, like a single self-aware brain, complete with false memories of a reality that never existed. If the universe is truly infinite, then Boltzmann brains, randomly appearing conscious minds, should vastly outnumber real, evolved beings like us. That means, statistically, it is more likely that you are a Boltzmann brain than a real person living in a real history. Everything you think you remember, your past, your life, even the universe itself, could be an illusion created in a brief, spontaneous moment of order before dissolving back into chaos. This paradox challenges the very nature of existence. If the laws of physics predict that random consciousnesses are more common than real observers, then why do we see a stable, structured universe instead of a fleeting hallucination? Some scientists argue that Boltzmann brains are a flaw in how we understand probability in an infinite universe. Others suggest that any theory predicting an observer more likely to be a solitary brain than part of a real universe must be fundamentally wrong. The Boltzmann brain paradox forces us to ask, are we truly living in a vast, evolving universe, or are we just temporary illusions that will vanish as suddenly as we appeared? Welcome to level 62 of 100 paradoxes. Imagine a tiny, invisible creature that could break the laws of physics just by opening and closing a door. This is Maxwell's demon, a thought experiment that seems to defy one of the most fundamental rules of the universe, the second law of thermodynamics. The second law states that entropy or disorder always increases over time. In simple terms, heat naturally flows from hot to cold, and systems become more chaotic rather than more organized. But what if a demon could cheat the system? Imagine a box divided into two sections with gas molecules moving randomly between them. Now, place a tiny demon at the door between the sections. Every time a fast-moving molecule approaches, the demon lets it pass in one direction. Every time a slow-moving molecule approaches, the demon sends it to the other side. Over time, one side of the box becomes hotter, while the other becomes colder, without adding any energy. This seems to reverse entropy, creating an orderly system out of randomness. But this is a paradox. If Maxwell's demon were possible, it would mean we could create a perpetual motion machine, something that works forever without energy input, something that the laws of physics say is impossible. Scientists debated this for years, but later discoveries showed that the demon itself must obey the laws of thermodynamics. To sort the molecules, it would need to gather information, store it, and eventually erase it. This process itself creates entropy, meaning the total disorder of the system still increases. Maxwell's demon forces us to ask, are the laws of physics truly unbreakable, or could information itself be the key to controlling entropy? Welcome to level 63 of 100 paradoxes. Two particles are created together, then sent in opposite directions. One to Earth, the other to the farthest reaches of space. Despite being light years apart, when one particle is measured, the other instantly responds. This is quantum entanglement, a phenomenon so strange that Einstein called it spooky action at a distance. In classical physics, information takes time to travel, limited by the speed of light. But in quantum mechanics, entangled particles seem to communicate instantly, no matter how far apart they are. Here's how the paradox works. 1. Two particles are entangled, meaning their properties, like spin, are linked. 2. Until measured, each particle exists in a superposition of possible states. 3. The moment you measure one particle, the other immediately takes on a corresponding state, even if it's on the other side of the universe. This defies our normal understanding of cause and effect. If no signal can travel faster than light, how does the second particle know what the first one's result was? Einstein believed this meant quantum mechanics was incomplete. He suggested there might be hidden variables, unknown factors that already determined the outcome before measurement. But in the 1960s, John Bell developed a test to prove whether hidden variables existed. Experiments confirmed that entanglement is real, and no hidden variables explain it. This paradox forces us to question the nature of reality. Is information traveling instantly, breaking the speed of light? Does measuring one particle somehow affect the past? Is reality fundamentally connected in ways we don't yet understand? One possible explanation is the idea that space itself might not be what we think. It could be that entangled particles are not truly separate, but exist as part of a deeper, hidden connection beyond three-dimensional space. The quantum entanglement paradox makes us ask, if two particles can be instantly linked across the universe, what does that say about the fundamental nature of reality? Welcome to level 64 of 100 paradoxes. Imagine a universe where everything that has ever happened will eventually happen again. Every moment, every thought, every event, repeating over an unimaginably long time scale. This is the strange implication of Poincaré recurrence theorem, a concept that challenges how we think about time, randomness, and the fate of the universe. Proposed by mathematician Henri Poincaré, the theorem states that in a finite system with fixed energy, given enough time, the system must eventually return to a state arbitrarily close to its original condition. To understand why, imagine a box filled with gas molecules bouncing around randomly. Over time, the molecules will explore every possible arrangement within the box. Since there are only a finite number of ways they can be arranged, eventually, by pure chance, they must return to a previous configuration, no matter how unlikely it seems. This idea applies not just to gas molecules, but to entire universes. If our universe is a finite system that follows deterministic laws, then over a long enough time scale, everything, every galaxy, every planet, even every thought you've ever had, will happen again. The paradox is that, in practice, this time scale is incomprehensibly huge. For a system as large as the universe, a full recurrence could take trillions upon trillions of years, far longer than the current age of the universe. This leads to deep philosophical questions. Does this mean time is an infinite loop? If everything repeats, do we have free will? Or is reality just playing on repeat? Could this be the explanation for déjà vu, echoes of past recurrences? Some scientists argue that the Poincaré recurrence theorem doesn't apply to our universe because of entropy, the fact that disorder always increases. But if the universe is truly a closed system, then recurrence is not just possible, it's inevitable. The Poincaré recurrence theorem forces us to ask, is the universe heading toward an infinite cycle of rebirths where everything we experience has already happened countless times before? Welcome to level 65 of 100 paradoxes. Imagine stepping into a futuristic teleportation machine. It scans your entire body, down to every atom, and transmits this data across space. On the other side, a perfect copy of you is reassembled. Same thoughts, same memories, same consciousness. But here's the question. Is that still you? This is the teletransportation paradox, a thought experiment that challenges the nature of identity, consciousness, and what it means to be you. The paradox works like this. You step into the teleportation machine. The machine scans and destroys your original body to avoid duplicates. The exact information is transmitted elsewhere and used to create a perfect replica of you. The new version of you steps out, remembering everything as if nothing happened. From an outside perspective, teleportation worked. Your body disappeared in one place and appeared in another. But if the original version was destroyed, what happened to your consciousness? Some argue that since the copy is perfect, your experience continues seamlessly, meaning teleportation is just a high-tech way of moving. Others argue that the original you ceases to exist, meaning every teleportation is actually a form of death, replacing you with a duplicate who only thinks they are you. This paradox raises unsettling questions. Is personal identity tied to physical continuity, or just to memories and patterns? If teleportation kills the original, is every copy a new person who only thinks they are the same? If consciousness is just information, could multiple copies of you exist at the same time? The teletransportation paradox forces us to ask, are we more than just the sum of our memories and atoms? And if a perfect copy of you exists, is there any meaningful difference between the original and the duplicate? Welcome to level 66 of 100 paradoxes. Imagine taking a solid sphere, like a basketball, and breaking it into a few pieces. Now, without stretching, shrinking, or adding anything, you rearrange those pieces, and suddenly you have two identical basketballs. This is the Banach-Tarski paradox, a mind-blowing mathematical result that seems impossible. It states that in the world of pure math, it is possible to take one object, split it into a finite number of pieces, and reassemble them into two objects of the same size as the original. Here's how it works. In everyday life, cutting something in half means each piece is half as big. But in higher-level mathematics, objects aren't just made of small parts. They are made of infinitely many points. The paradox takes advantage of this by dividing an object into non-measurable sets, collections of points so complex that they don't behave the way normal shapes do. The proof, developed by Stefan Banach and Alfred Tarski, relies on advanced set theory and the axiom of choice, a controversial rule in mathematics that allows for picking elements from infinite sets in ways that seem unintuitive. But before trying this on your basketball at home, here's the catch. This paradox only works in pure mathematics. In the real world, physical objects are made of atoms, and you can't separate them into infinitely complex sets. It challenges our basic ideas of size and volume. In normal geometry, when you cut an object, the total volume stays the same. But the Banach-Tarski paradox suggests that, mathematically, volume can be doubled. It suggests that infinity doesn't follow normal logic. If space itself were infinitely divisible in reality, could something like this actually happen on a cosmic scale? The Banach-Tarski paradox forces us to ask, if mathematical logic allows objects to duplicate, does that mean our understanding of space and matter is incomplete? And if infinity plays by different rules, what else might be possible in the world of pure mathematics? Welcome to level 67 of 100 paradoxes. Imagine trying to walk across a room. Before you reach the other side, you must first get halfway there. Then, before you can reach the end, you must travel half of the remaining distance. Then, half of that. And so on. Forever. This is Zeno's dichotomy paradox, a problem that suggests motion should be impossible. The logic is simple. To move from point A to point B, you must first get halfway. But before you reach that halfway point, you must first get halfway to halfway. No matter how close you get, there will always be another halfway point left to reach. Since there are infinite halfway points, it seems like you will never actually reach your destination. But in real life, people walk across rooms, arrows hit targets, and motion happens all the time. So, what went wrong? The paradox happens because it assumes that adding up an infinite number of steps must take an infinite amount of time. But in reality, the sum of all these steps can still be finite. For example, if you keep cutting the distance in half, the total distance adds up to 1. Even though there are infinite terms in the sequence, their sum still converges to a finite number, meaning motion is possible. This was formally solved using calculus, developed centuries later by Newton and Leibniz. Their work showed that an infinite series can have a finite sum, resolving Zeno's paradox mathematically. But the deeper question remains. If motion is continuous, does space itself break down into smaller and smaller parts forever? Is there a fundamental limit to how small distances can get? Or is the universe truly infinite in its divisibility? Does time itself flow smoothly, or does it jump in tiny increments like frames in a movie? Welcome to level 68 of 100 paradoxes. Imagine trying to measure a tiny particle, like an electron. You want to know exactly where it is and how fast it's moving. But no matter how precise your instruments are, the more you pin down one, the more uncertain the other becomes. This is Heisenberg's uncertainty principle, one of the strangest and most fundamental ideas in quantum mechanics. In classical physics, we expect to be able to measure anything with unlimited precision. If you track a moving car, you can measure both its speed and its location at the same time. But at the quantum level, this isn't possible. The uncertainty principle states that the more precisely you measure a particle's position, the less precisely you can measure its momentum, which is mass times velocity, and vice versa. The paradox is that this isn't just a problem with our measuring tools, it's a fundamental limit of nature itself. Here's why. 1. At the quantum level, particles behave like waves and particles at the same time. 2. A wave is spread out, meaning it doesn't have a single, precise position. 3. The more we force a particle to have a definite position, the more its wave properties get distorted, making its momentum highly uncertain. 4. Likewise, if we precisely measure momentum, the particle's location becomes spread out and uncertain. This means that reality isn't as clear-cut as we once thought. At the smallest scales, particles don't have exact positions and speeds until they are measured. They exist in a fuzzy, probabilistic state. This principle has massive implications. 1. It proves that absolute determinism is impossible. There is no way to predict the exact outcome of a quantum event. 2. It sets a limit on what can ever be known. Some things in nature are fundamentally unknowable, no matter how advanced science becomes. 3. It plays a role in everything from quantum computing to black holes. Even the energy of empty space fluctuates due to uncertainty. The uncertainty principle forces us to ask, If the universe itself is uncertain at the smallest level, how much of reality is truly predictable? And if reality depends on measurement, does that mean the act of observing changes the world around us? Welcome to level 69 of 100 paradoxes. Imagine an infinite hotel, a place with an unlimited number of rooms, all numbered 1, 2, 3, 4, and so on. Every room is occupied, but somehow the hotel can still accommodate new guests. This is Hilbert's infinite hotel paradox, but let's add a twist. What happens if half the guests leave? Normally, in a finite hotel, if half the guests leave, half the rooms would be empty. But in an infinite hotel, something strange happens. 1. Suppose every guest in an odd-numbered room leaves, so guests in rooms 1, 3, 5, 7, etc. are gone. 2. That means only guests in even-numbered rooms remain, rooms 2, 4, 6, 8, and so on. 3. Now, the hotel manager shifts each guest to a new room by dividing their old room number by 2. 4. The guest in room 2 moves to room 1. The guest in room 4 moves to room 2, and so on. After this simple shift, the hotel is once again completely full, even though an infinite number of guests left. This creates a paradox. An infinite hotel loses half its guests, but still remains full. The number of guests should have gone down, but in a way, it hasn't. Infinity behaves in a way that defies normal logic. You can take away an infinite number of things and still be left with an infinite amount. This paradox isn't just a weird thought experiment. It reveals deep truths about mathematics, set theory, and infinity itself. It forces us to ask, if removing half of infinity still leaves infinity, can infinity ever shrink? Does this mean infinite quantities are all the same size? Or are there different kinds of infinity? If space itself were infinite, could it work like Hilbert's hotel? The infinite hotel paradox with a twist shows us that infinity doesn't follow the rules of everyday numbers. Welcome to level 70 of 100 paradoxes. Now, let's dive into a paradox from the strange world of quantum mechanics, the quantum Zeno effect. Imagine you have a radioactive atom that is supposed to decay over time. Normally, it has a predictable half-life, meaning that over a given period, there's a certain probability that it will decay. But what if you keep measuring it constantly? Quantum mechanics tells us something shocking. The more you observe the system, the less it changes. If you repeatedly measure an unstable particle, you can actually freeze it in its original state. Instead of decaying as expected, it behaves as if it is stuck in time. The more frequently you check, the longer it takes to decay. This is known as the quantum Zeno effect, named after Zeno of Elea, the ancient Greek philosopher famous for his paradoxes of motion. Just like Zeno's paradoxes suggested that motion might be an illusion, the quantum Zeno effect suggests that change itself can be stopped just by the act of observation. But how does this work? It all comes down to the fundamental principle of quantum mechanics, the wave function. Before measurement, a quantum system exists in a superposition of multiple possible states. But the moment you measure it, the wave function collapses into a single definite state. Now, if you keep measuring the system rapidly, you are constantly forcing the wave function to collapse before it can evolve into a new state. As a result, the system remains frozen in its initial condition, preventing it from changing. This effect has been experimentally confirmed in physics labs. Scientists have been able to slow down or even completely halt atomic decay simply by increasing the rate of measurement. Welcome to level 71 of 100 paradoxes. Imagine uploading your mind into a computer, a perfect digital copy of your consciousness, complete with your thoughts, memories, and personality. The original you is still alive, but now a second version exists in a simulation. Now, here's the paradox. Which one is the real you? At first, the answer seems obvious. The original is real, and the copy is just data. But the copy thinks exactly like you, remembers your entire life, and believes it is the same person. Now, let's go further. What if, after the upload, the original version of you dies? Does your consciousness continue through the copy, or was you lost forever? Now, imagine the process is reversed. The digital copy is downloaded back into a new biological body, identical to your original self. Is this new version still you, or has a new person been created? This paradox exposes a major problem in identity and continuity. Are you just a pattern of information, or is your consciousness tied to a specific physical body? If a perfect copy of you can exist, does that mean you are no longer unique? If consciousness can be duplicated, does it prove that the idea of self is an illusion? One possibility is that identity is just an illusion of continuity. You feel like the same person from moment to moment, but there is no single, continuous you. Instead, you are just a process running on a biological machine. And if that process can run elsewhere, you still exist. Another perspective is that only the original experience's true consciousness and a copy, no matter how perfect, is nothing more than a simulation. Welcome to level 72 of 100 paradoxes. A man writes a simple sentence on a piece of paper. This sentence is false, or 2 plus 2 equals 5. At first glance, it seems like just another version of the liar paradox, where a sentence declares itself false, creating an endless contradiction. But this one is different. It adds an extra condition that makes the paradox even worse. If the sentence is true, then what it says must be correct. This sentence is false, or 2 plus 2 equals 5. But since 2 plus 2 does not equal 5, the first part must be true, meaning this sentence is false must be true. But that's a contradiction. If the sentence is false, then this sentence is false should be false. But that would make the whole sentence true because the second part, or 2 plus 2 equals 5, is still false. No matter how you look at it, the logic collapses into an infinite loop. Unlike the original liar paradox, where one sentence refers to itself, this version introduces an unrelated mathematical fact, making it harder to dismiss as a simple self-referential trick. This paradox, known as the liar's revenge, raises disturbing questions. Can truth and falsehood exist in a single statement at the same time? Does this mean some statements cannot be classified as either true or false? If logic itself can lead to paradox, does that mean it has limits? Some philosophers and logicians argue that statements like this reveal fundamental gaps in our understanding of truth, suggesting that reality may not be as black and white as we assume. Others believe paradoxes like these show the need for a new system of logic that allows for statements that are neither true nor false, but something in between. The liar's revenge forces us to ask, if contradictions like this can exist, how much of what we assume to be logical truth is actually stable? And if truth itself can be paradoxical, what does that mean for everything we believe to be real? Welcome to level 73 of 100 paradoxes. Imagine you're playing a game where the goal is simple. Follow the rules and make a move until the game ends. Most games, like chess or tic-tac-toe, are finite, meaning they always reach a conclusion. But now, let's define a new game called hypergame. On your turn, you can either choose to end the game or pick any well-defined game to play. If you choose a game, the players must finish it before returning to hypergame, where the next player makes their choice. At first, this seems completely normal, but here's where the paradox appears. If hypergame is a well-defined game, then you must be able to pick any well-defined game, including hypergame itself. Now, the game never truly ends. The first player picks hypergame again. The next player also picks hypergame. This can continue forever, meaning hypergame is an infinite game. But this is a contradiction, because by definition, hypergame was supposed to be a well-defined game, meaning it should always end. Instead, it creates a paradox by allowing itself to be picked, forming an infinite loop that never resolves. This paradox exposes deep problems in self-reference and recursion. Can a game truly contain itself? If so, what prevents an infinite loop? Does the definition of a game break down when it allows infinite recursion? Are there limits to what we can call well-defined? This is similar to Russell's paradox in set theory, where a set that contains all sets leads to contradictions. Likewise, hypergame seems to be both a finite game and an infinite one at the same time. Welcome to level 74 of 100 paradoxes. Imagine you're watching a security camera feed showing a quiet street. Nothing is happening, so you look away for a few seconds. When you look back, you see that a car has appeared on the screen. Here's the question. Did the car appear while you weren't watching, Or did it only exist once you looked again? This is the observer's dilemma, a paradox that plays with the nature of reality, time, and perception. It asks, does something exist when it isn't observed, or does observation itself create reality? At first, this seems like a simple issue. Of course, the car existed even when you weren't looking. But this paradox goes deeper. In quantum mechanics, the famous double-slit experiment shows that particles behave differently depending on whether they are observed. When unmeasured, they act like waves, existing in multiple states at once. When observed, they collapse into a definite position. In philosophy, Berkeley's idealism suggests that reality only exists when it is perceived. If no one is looking at the moon, does it still exist? Or does the act of perceiving bring it into being? In theoretical physics, some interpretations of reality suggest that time and space themselves may not exist independently of observation. The universe might only take on a definite form when measured. This paradox raises unsettling questions. If something isn't observed, can we ever be sure it exists? If observation affects reality, does that mean the world is shaped by our awareness? Does time itself move forward when unobserved? Or is it just an illusion created by the act of looking? Some physicists suggest that the universe might function like a giant quantum system, only solidifying into a definite state when measured. Others argue that reality is always there, but we only experience a fraction of what truly exists. The observer's dilemma forces us to ask, is the world around us truly independent, or do we play a larger role in shaping reality than we realize? Welcome to level 75 of 100 paradoxes. Imagine a machine that can erase specific memories from your mind, leaving everything else untouched. You decide to erase the memory of using the machine itself. Now, here's the paradox. If you don't remember using the machine, did you ever actually make the decision to erase your memory? This is the memory erasure paradox, a thought experiment that challenges the nature of free will, identity, and decision-making. At first, it seems simple. You made the choice, erased the memory, and moved on. But if you no longer remember making the choice, then, from your perspective, the event never happened. 1. Did you truly decide, or was the decision erased from history? 2. If you later question why you feel like something is missing, would you think you were ever given a choice at all? 3. What if someone else erased your memory? Would you ever know you had lost something? This paradox touches on deep philosophical and psychological problems. 1. The illusion of choice. If your memory of making a decision is erased, can you still claim to have made that decision? 2. The ship of Theseus problem applied to the mind. If parts of your memory are removed, at what point do you become a different person? 3. Self-referential loops. What happens if you keep erasing the memory of erasing your memory? Would you ever truly be able to track reality? Some argue that identity is tied to continuous memory. If memories define who you are, then erasing even one event means the version of you that made that decision no longer exists. Others suggest that the conscious mind works in real time, so even if the past is erased, it doesn't matter because the present self is still real. The memory erasure paradox forces us to ask, if you forget a decision, did you ever really make it? And if your memories define you, what happens when parts of your past are erased forever? Welcome to level 76 of 100 paradoxes. Imagine you flip a coin, but before you see the result, you take a pill that erases your memory of flipping it. A friend sees the result and tells you afterward, you flipped the coin, but you don't remember it. What do you think the outcome was? Logically, the coin still landed on heads or tails, just like any normal flip. But from your perspective, you have no evidence that the coin flip even happened at all. Now, here's the paradox. If you assume the flip happened, the probability should be 50-50, heads or tails. But if you have no memory of flipping the coin, do you have any reason to believe the event happened at all? If you repeat this experiment multiple times, and each time your memory is erased, can you ever be sure that any flips occurred? This paradox combines ideas from probability, memory, and perception. Probability without evidence. If you have no memory of an event, should you still assign it the same probability as if you remembered it? Self-consistency in time. If the past leaves no impact on your mind, does it still exist for you? infinite regress of forgotten events. If every time you flipped a coin, your memory was erased, would you ever be able to confirm that a single coin flip happened? This paradox is similar to Sleeping Beauty, but with a crucial difference. Instead of questioning probabilities based on repeated awakenings, it questions whether forgotten events can even be meaningfully assigned probabilities at all. Some philosophers argue that the past is real, regardless of memory. Just because you forget something doesn't mean it didn't happen. Others suggest that personal experience is what defines reality. So if you don't remember flipping the coin, it may as well have never happened to you. The forgotten coin flip paradox forces us to ask, if an event leaves no trace in your memory, can it still be considered real? And if all your past decisions were erased, would you still be the same person? Welcome to level 77 of 100 paradoxes. Mathematics is supposed to be precise, logical, and free from contradictions. But what if infinity itself refuses to behave the way we expect? This is Skollem's paradox, a mind-bending problem in set theory that challenges how we understand numbers, size, and even reality itself. In mathematics, there is a concept called countable infinity. This is the kind of infinity that includes all the natural numbers, 1, 2, 3, 4, and so on, forever. Even though this set is infinite, we can still list the numbers one by one. Then there is uncountable infinity, which is even larger. The real numbers, like pi, e, and irrational numbers, form an uncountable set, meaning there are more real numbers than there are natural numbers, even though both sets are infinite. Mathematician Georg Cantor proved this by showing that no matter how you try to list real numbers, there will always be some missing. So far, so good. But here's where Skollem's paradox comes in. In formal logic, we can describe the set of real numbers using mathematical rules. However, a theorem called the Löwenheim-Skollem theorem says that if a mathematical system has an infinite model, then it must also have a countable model, one where everything still works logically, but the uncountable real numbers somehow behave as if they are countable. This leads to a paradox. 1. The real numbers are uncountable. This is a fundamental mathematical fact. 2. But Skollem's theorem says that in some logical models, the real numbers can appear countable. 3. How can something be both countable and uncountable at the same time? This seems absurd. If a mathematical structure proves that uncountable numbers exist, how can we also create a logical system where those same numbers appear countable? Some mathematicians argue that this paradox isn't really a contradiction, but instead shows that formal mathematical descriptions can be tricky. Just because a model behaves a certain way, inside its own logic, doesn't mean it reflects the true nature of reality. Others suggest that it exposes deeper limits in how we define mathematical objects, questioning whether infinity itself is as rigid as we assume. Skollem's paradox forces us to ask, if math itself can describe an uncountable set as countable, how much of what we believe about numbers is just a result of the system we use? Welcome to level 78 of 100 paradoxes. Imagine standing in front of a bright light, casting a shadow on the wall. Now, imagine moving the light farther away. Your shadow gets bigger and stretches out, but it remains sharp and well-defined. Now, here's where the paradox begins. What if the light source were infinitely far away? Would your shadow become infinitely large? If so, does that mean your shadow is now covering the entire universe? At first, this might seem like a simple question about physics, but it reveals a deep paradox about infinity, perception, and existence. Shadows are cast when light is blocked by an object. If a light source is extremely far away, the shadow grows and spreads. But in an infinite universe, this leads to strange contradictions. If your shadow becomes infinitely large, does that mean it exists everywhere at once? Can something infinitely large still be called a shadow? Or has it become something else entirely? If light is needed for shadows, but light is infinitely distant, does the shadow even exist at all? This paradox isn't just a trick of the imagination, it ties into real questions in physics and philosophy. 1. The horizon problem in cosmology. If light takes time to travel, can any part of the universe truly see another part? 2. The nature of information spread. If a shadow grows infinitely, does it carry information forever? or does it fade into meaninglessness? 3. The concept of infinity in reality. If something stretches infinitely, is it still real in any meaningful sense? Some physicists argue that an infinitely large shadow doesn't make sense because shadows rely on contrasts. If everything is covered, is there really a shadow at all? Others suggest that infinity itself is an illusion, meaning that even though mathematics allows for infinitely large things, reality does not. The infinite shadow paradox forces us to ask, if something stretches across infinity, does it still exist as a single object, or does it dissolve into nothingness? And if a shadow can cover the entire universe, does that mean it is no longer a shadow at all? Welcome to level 79 of 100 paradoxes. Imagine you are given a 100% accurate prophecy of your future. The prophecy tells you exactly what will happen tomorrow, down to the smallest detail. But there's a catch. As soon as you read the prophecy, you will forget it. Now, here's the paradox. The future is predetermined, since the prophecy is always right. But you don't remember the prophecy, so you make decisions as if you don't know the future. If you don't know the future, are you still following a predetermined path, or are you acting freely? This is the forgotten future paradox, a thought experiment that challenges the relationship between determinism, free will, and memory. At first, it seems like free will still exists. Since you don't remember the prophecy, you experience choice as if you are making your own decisions. But since the prophecy is never wrong, that means every decision you make must align with it. Are you truly choosing, or just acting out a script? If forgetting the future still leads you to the same outcome, does knowing it even matter? Does memory determine free will, or does it only create the illusion of control? This paradox connects to deep questions in physics, psychology, and philosophy, quantum mechanics, and the block universe. If time is just another dimension, does that mean our future is already set, and we are just experiencing it step by step? Neuroscience of memory and identity. If you forget an event, does that mean it never affected you? How much of free will depends on remembering our choices? Predestination versus free will. If everything is already written but we can't remember it, does that mean we are both free and bound at the same time? Some argue that free will is an illusion, and whether or not we remember a choice, it was always going to happen. Others suggest that memory itself is what makes decisions feel real, meaning without it, our choices might not even exist. The forgotten future paradox forces us to ask, if the future is set, but we don't remember it, are we still making choices? And if forgetting changes nothing, does knowing the future actually matter? Welcome to level 80 of 100 paradoxes. Omnipresence is the idea of being everywhere at once, an all-encompassing presence that exists in all places, at all times, without limits. It sounds like the ultimate power, but when examined closely, it leads to contradictions that challenge whether it is even possible. If something is truly everywhere, does that mean it occupies every space, no matter how small? Can it fit inside the tiniest possible area, or is it stretched infinitely thin? If it exists in all locations at once, is there any meaningful difference between one place and another? And if it takes up all space, where does that leave everything else? This leads to a strange contradiction. If omnipresence means fully existing in every possible place, then it must exist in paradoxical locations, inside a black hole where physics breaks down, in a place with no space at all, like the quantum vacuum, or even in logically impossible locations, such as a shape with zero volume. Can something exist everywhere, even where existence itself is undefined? Then comes another problem. If a being is everywhere, does that mean it is everything? If it has no single location, can it have any distinct identity at all? If omnipresence means occupying all space, then how is it different from space itself? If it exists in all things, is it separate from them? Or is everything just a part of it? This also raises a question about free will. If an omnipresent being is in your mind, does it experience your thoughts as its own? If yes, then every thought, good or bad, belongs to it. But if no, then there must be some space where it does not exist, contradicting the idea of omnipresence. Some suggest that omnipresence doesn't mean being in all places in the same way. It could mean being able to access or interact with all places without physically occupying them. Others argue that omnipresence is a concept beyond human logic, and isn't meant to be understood in spatial terms. The paradox of omnipresence forces us to ask, can something truly be everywhere without contradiction, or does the very idea collapse under its own definition? Welcome to level 81 of 100 paradoxes. Imagine that technology has advanced to the point where immortality is possible, but with a catch. Instead of making your current body live forever, the process transfers your consciousness into a new body every time you are about to die. At first, this sounds like a perfect solution. Every time your body fails, you simply wake up in a fresh, healthy one. Your thoughts, memories, and personality all remain intact. You never die. But here's the paradox. Are you actually immortal, or are you just being replaced by a perfect copy each time? If the process works by copying your consciousness into a new body, does that mean the original you ceases to exist every time the transfer happens? If so, then every version of you only lives once, and the real you dies each time, meaning no single person is actually immortal. But if your consciousness is truly continuous, then what happens if a glitch in the system creates two copies at the same time? Now, both versions wake up believing they are the real you. Which one is actually you? If both have your memories and identity, did you just duplicate yourself, or did the process create a new person each time? This paradox exposes deep problems in how we define identity and continuity. If your consciousness can be copied, is there such a thing as a real you? If two copies exist at the same time, which one is the true continuation of your existence? Does the survival of your memories mean you are still alive, or is the original version of you dying each time without realizing it? Some argue that identity is just a pattern. If your thoughts and memories persist, you are still you. Others say that consciousness is tied to a single, unbroken experience, meaning that if you are replaced by a copy, the original you is gone forever. The immortality transfer paradox forces us to ask, does immortality really mean never dying, or just being continuously replaced? And if every version of you thinks they are the real one, does it even matter? Welcome to level 82 of 100 paradoxes. Knowledge is supposed to be simple. If you believe something, if it is true, and if you have justification for believing it, then it seems like you know it. For centuries, this was the standard definition of knowledge, justified true belief. But in 1963, philosopher Edmund Gettier proposed a problem that shook this definition to its core. Imagine this. You're walking through a town filled with fake barns, hollow structures designed to look like real barns from the road. By chance, you look at the only real barn in the entire area and think, that's a barn. Your belief is true. It really is a barn. Your belief is justified. You saw it with your own eyes. But did you actually know it was a barn? Here's the problem. If you had looked at any other barn in the area, you would have been wrong. Your belief was true by accident, not because of any reliable reasoning. This is the Gettier problem. It proves that justified true belief is not enough for knowledge. Let's try another example. Suppose your friend owns a dog, and you believe they have a dog. But one day they secretly give their dog away and immediately adopt an identical-looking one. You still believe they have a dog. Your belief is true. They do own a dog. Your belief is justified. You see the dog all the time. But your belief was based on the wrong evidence. You thought they still had their original dog. So, did you ever really know they had a dog? Gettier's argument proves that knowledge requires something more than just belief, truth, and justification. But what? Some philosophers suggest we need an extra condition, such as requiring that knowledge must not be based on luck. Others believe that certainty is impossible, and we should redefine knowledge entirely. The Gettier problem forces us to ask, how can we ever be sure we truly know something? If knowledge can be justified, true, and still wrong, then what separates knowledge from lucky guesses? Welcome to level 83 of 100 paradoxes. Imagine waking up one morning with the strange feeling that you had a dream, but you can't remember anything about it. It's gone, vanished from your memory. Now, here's the paradox. If you can't remember the dream, did you ever actually have it? Dreams feel real when we experience them, but once they fade from memory, what proof do we have that they ever happened? If no trace of the dream remains in your mind, is there any difference between a forgotten dream and a dream that never happened at all? This is the paradox of the forgotten dream. a thought experiment that challenges how we define experience, memory, and reality itself. At first, it seems like the answer should be simple. If you had a dream, even if you forgot it, it still happened. But think about this. If an experience leaves no trace, did it ever really exist? If you never recall the dream, how is it different from a dream that never occurred? Is memory the only thing that makes an event real? This paradox has deep implications for consciousness and reality. If we expand this idea beyond dreams, it raises unsettling questions. What if we forget major moments in our lives? Do they still define us if we have no memory of them? If you were told that an event happened but had no recollection of it, how could you ever be certain it was real? If all of history were forgotten, would it still have happened in any meaningful way? Some philosophers argue that memory is what makes an experience real. If you can't recall it, it might as well have never happened. Others suggest that events don't depend on memory at all. They exist whether we remember them or not. The paradox of the forgotten dream forces us to ask, is reality defined by what we remember, or does it exist independently of our awareness? And if an experience disappears completely from memory, is it any different from one that never existed? Welcome to level 84 of 100 paradoxes. Probability seems like a straightforward concept. Events have chances of happening, and we can calculate those chances with the right information. But what if probability could change based on how we describe the same event? This is the Borel-Kolmogorov paradox, a problem in conditional probability that shows how our understanding of likelihood can shift depending on perspective. Imagine a sphere, like Earth, and randomly select a point on its surface. Now, let's calculate the probability that this point lies on the equator, given that we already know it's on some specific line of latitude. At first, this seems easy. If we assume a uniform probability distribution across the sphere, then every latitude line has an equal chance of being chosen. And since the equator is just one of many latitude lines, the probability of our selected point being on the equator should be 0, just like choosing an exact point from an infinite set. But now, let's describe the same problem differently. Instead of choosing a latitude first, imagine that we randomly pick a longitude, a vertical line running from the North Pole to the South Pole. Since every longitude line crosses the equator, and all longitudes are equally likely, the probability of landing on the equator suddenly seems to be 1 instead of 0. This is the paradox. The probability of the same event, choosing a point on the equator, changes depending on how we approach the question. The reason this happens is because of how probability distributions work on continuous spaces. Depending on whether we condition the probability by latitude or longitude, the outcome changes. This reveals a deeper issue. If probability depends on how we frame a question, is it truly objective? Can there be multiple correct probabilities for the same event? Does this mean probability is just a tool of description rather than an absolute truth? Some argue that paradoxes like this show the limits of probability theory when applied to infinite sets. Others suggest that probability isn't an intrinsic property of reality, but a way for us to model uncertainty based on how we define our conditions. The Borel-Kolmogorov paradox forces us to ask, is probability an absolute truth, or does it shift based on perspective? And if the same event can have different probabilities, what does that mean for how we understand chance itself? Welcome to level 85 of 100 paradoxes. Imagine a world where everyone is happy. The people in this world live fulfilling lives, experience joy, and have all their basic needs met. Now, imagine a second world where the population is much larger, but while everyone is still happy, their happiness is less intense. Their lives are just barely worth living. Which world is better? This is the mere addition paradox, a problem in ethics and population philosophy that challenges how we think about well-being, morality, and the value of life itself. At first, it seems obvious that the first world is better. Fewer people, but each one experiences a high level of happiness. But now, let's add a simple twist. Take the first world and add more people who have lives that are barely worth living, not suffering, but just above neutral. The total happiness in the world has increased because now more people are experiencing at least some joy. If we keep repeating this process, we eventually reach a world where a massive population exists, but each individual has a very low level of happiness. This leads to an unsettling conclusion, called the repugnant conclusion, that a world with billions of people barely experiencing happiness could be considered morally better than a world with fewer people living extremely good lives. But is this really true? On one hand, total happiness has increased, so if we believe morality is about maximizing well-being, then adding more people, even if they are only slightly happy, seems like the right choice. On the other hand, this seems absurd. At some point, we might end up with an enormous population of people whose lives are just barely tolerable. Yet we are forced to call this better than a world where fewer people live truly great lives. This paradox challenges the way we define ethical decision-making. Is it better to have more people with lower happiness or fewer people with higher happiness? Does the total amount of happiness matter more than the quality of individual lives? If mere addition leads to a repugnant conclusion, does that mean our moral reasoning is flawed? Some philosophers argue that this paradox exposes the limits of utilitarianism, which focuses on maximizing happiness without considering individual well-being. Others suggest that quality of life matters more than total happiness, but struggle to explain why adding barely happy people is wrong. Welcome to level 86 of 100 paradoxes. Imagine you are standing in front of two doors, each leading to a different future. One leads to a life of happiness and success, the other to struggle and hardship. You must make a choice. But here's the twist. You are outside of time. Your decision has already been made in the future, but you haven't experienced making it yet. Now, here's the paradox. If the choice is already determined, do you still have free will? And if you are free to choose, how can the future already be set? This is the paradox of the timeless choice, a problem that challenges the nature of free will, determinism, and time itself. At first, it seems like a simple question. Either you have control over your choice or the outcome is fixed. But what if both are true at the same time? If the future already contains your decision, then your choice is predetermined. But in the present, you still feel like you have the power to choose freely. How can both be true? This paradox connects to major ideas in physics and philosophy. 1. Block universe theory. Some scientists believe time is like a book. Every page already exists, meaning the past, present, and future are all equally real. If that's true, then your choice is already written, even though you haven't reached that page yet. 2. Quantum mechanics. Some interpretations of quantum physics suggest that multiple futures exist, but the moment you observe one, it collapses into a single reality. 3. Fate versus free will. If your future is known, does that mean you are merely following a script? Or does your choice create the future in real time? Some philosophers argue that free will is an illusion. You only feel like you're making a choice, but in reality, it was always going to happen that way. Others believe that choices shape reality, meaning the future does not truly exist until the moment you decide. Welcome to level 87 of 100 paradoxes. Imagine you are watching a security camera feed of a locked, empty room. The screen shows nothing unusual, just an empty chair, a blank wall, and silence. But then, the feed cuts out for a single second. When it comes back, everything looks exactly the same. Now, here's the paradox. How do you know nothing changed while the feed was off? This is the observer vanishing paradox, a thought experiment that challenges how we define reality when we are not observing it. From your perspective, the room appears to be unchanged, but since you didn't witness that missing second, anything could have happened. A person could have entered and left. The chair could have disappeared and reappeared. Reality could have collapsed and restarted, leaving no trace. This paradox connects to deep ideas in physics, philosophy, and perception. 1. Quantum mechanics and the observer effect. In quantum physics, particles don't have definite properties until they are observed. Could the same apply to everyday reality? 2. The tree falling in a forest problem. If something happens where no one is watching, can we say it really happened? 3. Simulation theory. If reality behaves like a simulation, is it only rendered when observed? Could the missing second have been an error in how reality is processed? Some argue that reality is independent of observation, meaning the room remained unchanged whether or not you saw it. But others suggest that existence is tied to perception, meaning that for that missing second, the room had no definite state at all. The observer vanishing paradox forces us to ask, is reality always there, or does it only exist when we observe it? And if there are gaps in our awareness, can we ever truly know what happens when no one is watching? Welcome to level 88 of 100 paradoxes. Imagine a small, intelligent being, Maxwell's demon, who can cheat the laws of physics. He sits at the door between two chambers of gas, carefully opening and closing a tiny trapdoor. Every time he sees a fast-moving molecule, he lets it pass to one side. Every time he sees a slow-moving molecule, he keeps it on the other side. Over time, one side gets hotter and the other gets colder, creating a temperature difference without using any energy. This seems to violate the second law of thermodynamics, which says that entropy, disorder in a system, must always increase. But physicists later found a catch. Maxwell's demon doesn't just sort molecules, he must also store and process information about them. Now, let's add a new problem. What happens if the demon forgets? This is Maxwell's demon with information loss, a paradox that connects physics, computation, and entropy in a completely new way. If the demon keeps track of every molecule forever, he seems to cheat thermodynamics. But real systems can't store information perfectly. At some point, the demon's memory fills up, and he must erase old information to keep working. And here's the crucial twist. Erasing information creates entropy. In 1961, physicist Rolf Landauer discovered that whenever information is erased, heat is released, increasing disorder in the system. This means that no matter how perfectly Maxwell's demon sorts molecules, he must eventually delete old data, which restores entropy and prevents a perpetual motion machine. This paradox forces us to rethink not just physics, but also computation. If information is a physical thing, does memory storage itself obey thermodynamic laws? If forgetting increases entropy, does that mean every act of memory loss creates heat? Does this mean intelligence and computation are fundamentally linked to energy consumption? Some scientists argue that the universe itself may be like Maxwell's demon, constantly processing and erasing information. Others suggest that entropy is not just about disorder, it is directly tied to the limits of knowledge. Welcome to level 89 of 100 paradoxes. Imagine two scientists conducting an experiment in a high-tech lab. One scientist, Alice, stands inside an isolated chamber where an event will take place. A flash of light triggered by a quantum particle. The other scientist, Bob, stands outside the chamber, observing the results on a screen. Now, here's the setup. Inside the chamber, Alice sees the flash of light and records the time it happens. Outside the chamber, Bob's screen updates a few seconds later, confirming that the light flashed. But now, something strange happens. A glitch in the system erases Alice's memory of seeing the light. She checks her notes and finds no record of the flash happening. From her perspective, it never happened at all. Bob, however, still has the data on his screen proving that the event occurred. Now, here's the paradox. Did the event actually happen if one observer has no record of it? And if reality is observer-dependent, which observer is correct? This is the observer-dependent causality paradox, a problem that challenges the very nature of cause and effect. At first, it seems like a simple mistake. Alice just forgot. But in quantum mechanics, an event's existence can depend on whether or not it was observed. If Alice has no record of seeing the light, then as far as she is concerned, it never happened. But Bob's observation says otherwise. Welcome to level 90 of 100 paradoxes. Imagine watching a short video of people passing a basketball. Your task is simple. Count how many times the players in white shirts pass the ball. You focus, tracking every movement carefully. At the end of the video, you confidently give your answer. But then the researcher asks, "Did you see the gorilla?" Confused, you watch the video again, this time without counting. To your shock, a person in a gorilla suit walks into the scene, beats their chest, and walks away. You never even noticed. This is the invisible gorilla experiment, a psychological paradox that reveals a flaw in how we perceive reality. It proves that we don't see everything. We only see what we expect to see. At first, this seems like just a trick of attention, but the implications go much deeper. If we can completely miss something as obvious as a gorilla, what else are we missing in everyday life? Welcome to level 91 of 100 paradoxes. Knowledge seems limitless. There are truths about the universe waiting to be discovered, and in theory, anything that is true can eventually be known. But what if that idea is wrong? This is Fitch's paradox of knowability, a paradox that suggests there are truths that are fundamentally unknowable, even if they are logically possible to know. At first, this seems strange. The basic idea of knowability is that for any true statement, there must be a possible way for someone to learn it. This means that if something is true, we should at least be able to discover it. If not now, then in the future. But here's where the paradox happens. Let's assume there is a true statement that no one has ever known. That means the statement is both true because reality doesn't change based on what we know, unknown because no one has ever discovered it. Now, if everything that is true can be known, then this unknown truth must be knowable. But the moment someone learns it, it is no longer an unknown truth. It becomes a known truth. And here's the contradiction. If the statement must be knowable, but can only remain true if it is unknown, then it can never actually be known. Welcome to level 92 of 100 paradoxes. A famous thought experiment asks a simple question. If a ship's wooden planks are gradually replaced one by one until none of the original wood remains, is it still the same ship? This is the ship of Theseus paradox, a problem about identity and continuity. But now, let's take this idea and push it to the quantum level, where things get even weirder. Imagine that instead of a ship, we ask this about you, your body, your mind, and even the smallest particles that make you. On a basic level, the atoms in your body are constantly being replaced. The cells in your skin, your organs, even your brain, are not the same as they were years ago. The particles that make up your body today were once part of other things: stars, air, water, plants. So, if every part of you has changed, are you still the same person? Now, let's take this further. In quantum mechanics, identity is not as fixed as we assume. 1. Quantum superposition. A particle doesn't have a single definite state until it is observed. Could the same be true for identity? Do you exist in multiple versions until reality forces one into being? 2. Quantum entanglement. If two particles become linked, they share information instantly across any distance. If your atoms interact with the world constantly, is you just an evolving web of connections rather than a fixed identity? 3. Quantum tunneling. In rare cases, particles can teleport across barriers without crossing the space in between. If your particles are constantly shifting, is the version of you right now even the same one that existed a moment ago? This creates a paradox. If classical physics struggles to define the same ship after gradual change, quantum mechanics makes identity even more unstable. If particles are interchangeable and constantly replaced, then are you a continuous self, or just a pattern that persists for a while? Some physicists and philosophers argue that identity is not about the matter itself, but about the information and structure that remains over time. In this view, the ship of Theseus remains the same because its form persists, even if its parts are swapped out. The same could apply to you. Your consciousness and memories are what matter, not the specific atoms that make you up. Others suggest that true identity does not exist at all. Just like quantum particles, we are constantly shifting, never truly the same from moment to moment, meaning the idea of a stable self is just an illusion. Welcome to level 93 of 100 paradoxes. Imagine waking up one morning to find that everything feels slightly off. The people you know act the same, your house looks identical, and the world functions normally. But something is different. Then you check the news and realize something impossible. Every recorded event in history has been reversed. Wars were fought backward, buildings were constructed by collapsing in reverse, and rivers have flowed upstream, yet nobody seems to notice. Now, here's the paradox. If reality had always been reversed, would we even be able to tell? This is the reversed reality paradox, a problem that questions whether we can ever truly know the nature of time, memory, and causality. At first, it seems obvious that we would notice. After all, time moves forward and we remember the past. But what if our memories are also reversed? If every event played backward but our memories updated to match, we would still believe time was moving forward. If cause and effect flipped, we would perceive them as normal because our understanding of before and after would also be reversed. If this reversal had always been the case, then there would be no way to compare it to anything else, meaning we would accept it as reality. This paradox raises deep questions. Is time truly moving forward, or is that just an illusion created by memory? If we only experience time in one direction, how can we ever prove that's the right way? Would reversed reality be any different from normal reality if all perception adjusted to match? Welcome to level 94 of 100 paradoxes. Mathematics describes everything in the universe, from the motion of planets to the structure of atoms. But what if mathematics is the universe? This is Tegmark's mathematical universe hypothesis, a radical idea proposed by physicist Max Tegmark, which suggests that the universe itself is nothing more than a mathematical structure. At first, this might sound strange. We usually think of mathematics as a tool, a way to describe reality. But Tegmark argues that mathematics is not just a description. It is the fundamental nature of reality itself. Look at the laws of physics. The equations that govern gravity, electromagnetism, and quantum mechanics are deeply mathematical. The constants of nature, like the speed of light or the charge of an electron, seem to be numbers woven into the fabric of existence. But Tegmark takes this one step further. Instead of saying the universe follows mathematical laws, he suggests that the universe itself is a mathematical object. Think of a perfect circle. In the abstract world of mathematics, a circle has an exact radius, an exact circumference, and follows precise rules. According to Tegmark, the universe is just another mathematical shape. Complex, yes, but fundamentally no different from a geometric object. If the universe is purely mathematical, then 1. Everything, including space, time, and even consciousness, is just numbers and relationships between them. 2. The laws of physics are not rules imposed on reality, they are reality. 3. If mathematics exists outside of time and space, then the universe itself may be timeless and infinite. If all mathematical structures exist, then there should be universes for all possible mathematical systems. This means that our universe is just one mathematical structure among infinitely many. Other universes could follow completely different mathematical rules. The idea of a multiverse might not just be a sci-fi theory. It could be an unavoidable consequence of mathematics itself. Some critics argue that just because mathematics describes reality well, it doesn't mean reality is mathematics. They suggest that mathematics is a language, not the thing itself. Others question whether consciousness and experience can emerge purely from mathematical structures. Welcome to level 95 of 100 paradoxes. Imagine waking up in the morning, feeling the warmth of the sun on your skin, hearing birds outside, and smelling fresh coffee. Everything feels real, but what if none of it actually exists? What if you were just a brain, floating in a vat, hooked up to a powerful computer that simulates your entire reality? This is the brain in a vat paradox, a modern version of Descartes' evil demon thought experiment, and one of the most disturbing challenges to our understanding of reality. If your brain were removed from your body and placed in a vat of nutrients while a supercomputer fed it electrical signals that perfectly simulated your senses, you would experience life exactly as you do now. The sky, the ground, your own body. All of it could just be a simulation. At first, this seems impossible. But if a computer could perfectly replicate every sound, sight, and feeling, how would you ever be able to tell the difference? Everything you know about reality comes through your senses, but if those senses could be manipulated, then how can you ever prove that the world you experience is real? This paradox raises unsettling questions. If all experiences could be simulated, then what does it even mean to know something? How can we trust anything we perceive? Some philosophers argue that it doesn't matter. Even if you were a brain in a vat, your experiences would still be real to you. Others suggest that without a way to prove external reality, we can never be certain of anything beyond our own thoughts. This isn't just a thought experiment. It connects to modern science. Neuroscientists have already manipulated brain signals to create artificial sensations, proving that perception can be altered. Welcome to level 96 of 100 paradoxes. Imagine shining a beam of light through a complex experiment, knowing that how you choose to measure it will determine what happens. But here's the twist. You make the decision after the light has already passed through part of the setup. This is Wheeler's delayed choice paradox, a mind-bending thought experiment in quantum mechanics that suggests the past isn't fixed until we observe it. To understand how strange this is, we need to go back to the double-slit experiment. When light passes through two slits and is not observed, it behaves like a wave, interfering with itself and creating a pattern on a screen. But when we observe which slit the light goes through, it behaves like a particle, and the interference disappears. Now, what happens if we wait until after the photon has passed the slits to decide whether to measure it as a particle or a wave? This is exactly what physicist John Wheeler proposed. In the delayed choice experiment, a photon is sent toward a setup where it can take multiple paths. But instead of deciding how to measure it beforehand, we wait until after the photon has passed the decision point to determine whether we measure it as a wave or a particle. Logically, it should already know whether it behaved like a wave or a particle before we made the choice. But experiments show something unbelievable. Our decision in the present retroactively changes the photon's past behavior. If we measure for wave-like behavior, the photon seems to have taken multiple paths. If we measure for particle-like behavior, it seems to have taken only one path, as if it had always been a particle. This raises unsettling questions about the nature of reality. Does the past only exist when we look at it? If our choices in the present can affect the past, what does that mean for causality itself? Some physicists argue that quantum events don't have definite properties until they are observed, meaning the past isn't real until we look at it. Others suggest that reality is fundamentally connected across time, meaning that what we call the past is just another part of the equation, waiting to be determined. The Wheeler's delayed choice paradox forces us to ask, if the past isn't set until we observe it, does that mean time itself is not what we think? And if reality is shaped by our choices, are we constantly rewriting history without even realizing it? Welcome to level 97 of 100 paradoxes. Imagine a world where technology has advanced so far that every major decision, political, ethical, and scientific, is made through a perfectly fair AI system. This AI doesn't force people to obey it. Instead, it calculates the most rational and optimal decision for everyone. The AI provides pure, objective truth, decisions that no logical person can dispute. Now, here's the paradox. What happens when someone disagrees? If the AI always reaches the perfect decision, then any disagreement must mean that the person is irrational, uninformed, or acting against the common good. Over time, as people learn to trust the AI's conclusions, fewer and fewer people even try to argue against it. But at what point does perfect agreement stop being free choice and start becoming a new kind of control? If an idea is so obviously correct that no one opposes it, does that mean people are actually thinking for themselves, or are they just following the AI's decisions without question? This paradox raises deep philosophical and ethical questions. If an AI always makes the best decision, does disagreeing with it mean you are automatically wrong? If everyone follows the AI's choices, does free will still exist, or has it been replaced by unstoppable consensus? Can a world where everyone freely agrees actually be a form of hidden control? This connects to real-world issues in technology, governance, and decision-making. Algorithms already shape what we see, what we buy, and even what we believe. As AI systems get better at predicting optimal outcomes, will people slowly stop questioning them? Welcome to level 98 of 100 paradoxes. Imagine that you are trapped inside a perfect simulation. Every moment, every thought, and every action you take is part of a system designed to keep you inside. But you don't know it. To you, this world is all there is. Now, here's the paradox. If you were inside a perfect system that controlled your perception, how would you ever know? And if you did figure it out, how could you ever escape? This is the paradox of the observer's escape. A problem that suggests that if reality were designed to prevent you from realizing the truth, then even the idea of escaping might itself be part of the illusion. At first, it seems possible to break free. If something about reality felt off, glitches in perception, contradictions in physics, strange patterns, you could start investigating. But if the system were truly perfect, then it would control your perception completely, meaning even noticing a flaw would be impossible. It would generate explanations for anything unusual, preventing you from realizing the truth. If you ever got close to escaping, it could simply adjust your thoughts to make you forget you were questioning it in the first place. This paradox has deep implications for consciousness, reality, and free will. If you are part of a system that prevents you from knowing it exists, then how can you ever be certain that anything you believe is truly real? Even the concept of escaping could be an illusion, a carefully crafted way to make you think you have free will while keeping you inside the system. Now, take this idea further. Suppose you did manage to escape. How would you ever know that you weren't just inside a larger system, one designed to make you believe you had escaped? If every attempt at leaving simply places you inside a higher-level simulation, does escape even exist? Some argue that this paradox suggests true objectivity is impossible, that we can only ever experience reality as it is presented to us, meaning we can never step outside to see the full picture. Others suggest that if reality is self-consistent and allows us to question it, that's proof enough that we are not trapped. The paradox of the observer's escape forces us to ask, if we can only perceive reality from inside it, can we ever truly understand it? And if escape is impossible to confirm, does that mean we were never trapped in the first place? Or does it mean we always have been? Welcome to level 99 of 100 paradoxes. Imagine looking up at the night sky, staring at the stars, the galaxies, and the vastness of space. No matter how far our telescopes can see, there is always more beyond, an unfathomable cosmic expanse stretching into infinity. But here's the question. What if most of the universe is completely unobservable, not just because it is too far away, but because it exists in a way we can never perceive? This is the unobservable universe paradox, a problem that challenges whether reality itself is even measurable. At first, it seems simple. The observable universe, the part we can see, is limited by the speed of light and the expansion of space. Beyond that, galaxies exist, but their light will never reach us. That means there is an unobservable region of the universe that we will never be able to study. But now, take this idea even further. What if the majority of reality doesn't just exist beyond our telescopes, but in forms that are entirely outside our perception? 1. Extra dimensions. Physics suggests that there could be dimensions beyond the 3 of space and 1 of time we experience. If higher dimensional beings existed, we would never be able to see them directly, even if they were all around us. 2. Dark matter and dark energy. 95% of the universe is made up of something we cannot see, detect, or fully explain. If we can't observe it directly, how do we know if we are even measuring the full extent of reality? 3. Different laws of physics. Some theories suggest that other parts of the universe might have completely different fundamental forces. If physics itself varies across the cosmos, could entire regions of reality exist that follow rules so alien that we would never be able to recognize them? Now comes the paradox. If most of reality is unobservable, does it even exist for us? Some argue that what we cannot measure should not be considered real, since reality must be testable to be meaningful. Others suggest that our tools are simply too limited, and that vast portions of existence may forever remain outside our ability to comprehend. Welcome to the final level of 100 paradoxes. Everything we know is built on logic, reason, and explanation. We define concepts, create systems, and uncover truths. But what happens when we try to explain everything? This is the paradox of everything, a contradiction that challenges whether the universe, reality, and even logic itself can ever be fully understood. At first, it seems possible. Science, philosophy, and mathematics have given us deep insights into how the universe works. But as we go deeper, we run into a problem. Can everything be explained, or must some truths always remain beyond reach? Consider these contradictions. 1. The explanation problem. If everything requires an explanation, what explains the universe itself? If we say something caused it, what caused that? Does the chain of explanations go on forever? or does it eventually stop at something unexplainable? 2. The limits of logic. If logic is how we understand reality, then logic itself must be part of reality. But can logic explain why logic works? If everything must be proven, how do we prove the system that allows proof? 3. Self-contradiction of totality. If we try to define everything, we must also include things that are beyond definition. But if something is beyond definition, it cannot be part of everything. Now, let's take it further. If every paradox can be explained, then paradoxes themselves must have a logical resolution. But if paradoxes are, by definition, statements that defy logic, then explaining them removes their paradoxical nature, which means they were never paradoxes in the first place. So, does that mean paradoxes don't exist, or does it mean some truths cannot be resolved by logic at all? Some philosophers argue that total knowledge is impossible. There will always be questions that cannot be answered because any explanation requires a framework, and that framework must itself be explained. Others suggest that everything can be known, but not all at once, meaning total understanding is only impossible from a limited perspective. The paradox of everything forces us to ask, can reality ever be fully explained, or will some truths always remain unknowable? And if paradoxes must be explained, does that mean paradox itself is an illusion?